In this chapter, we're going to look at the energy changes that occur during a chemical reaction. When you analyze energy changes during a process, this is thermodynamics. Applying it to chemistry, in this chapter we call it thermochemistry. We're going to look at what happens during the reaction and look at the net result. The information we're going to learn in this chapter will serve as a foundation, so that means we got to study extra hard for chapters 2nd and 3rd quarter when we look at things such as equilibrium. Looking at energy changes, what occurs during a process, knowing that information allows you to predict a lot of things, allows you to understand why certain reactions happen and some don't. Before we begin this chapter with chemistry concepts, I'm going to give us a potential energy analogy using the Earth and the Moon. So let's say we have the Earth and there's some object X that's on the Earth. Relative to its position from the Earth's surface, it has a certain potential energy. So over here I'm going to make a kind of a diagram, and here's potential energy. And whatever the exact number is, here's where the object is on some potential energy scale. As that object moves away from the Earth and into outer space, anytime you move two objects that are attracted to each other further away, the potential energy increases. You have more potential energy on the 3rd floor of a building than on the 2nd floor. The first line on the potential energy scale, that's when the object is on the Earth. And there'll be a second line when it's away from the Earth. So it's left the Earth. It's at a higher potential energy. Let's just say that object fell onto the Moon. As that object fell onto the Moon, it would lose some of the potential energy it had gained as it moved further away from the Earth. So it required an input of energy to leave the Earth, and it gained potential energy. When it falls onto the Moon, it loses some, but it doesn't lose quite as much energy, quite as much of its potential energy as it gained from leaving the Earth. So its in position when it's on the Moon would be there. This is showing an energy change during a process. And this easily could have been an example of a redox reaction where some atom took an electron away from another atom. It requires energy to pull an electron away from an atom. Energy is released when that electron falls into the orbit of another atom. The net change of the process, if we look at potential energy, is this part right there, from the Earth to the Moon. That's the net change of potential energy. But during the process, you had to gain a lot more energy than what was released. So there's a process, and then there's a net to the process. But if this Earth to the Moon of an object was a chemical reaction, would this reaction, if this was done in a test tube, feel hot or feel cold? Well, the net change is that it had to take in some energy, so this reaction would have to take in energy from the surroundings, and it would feel cold if you did this in a test tube. You could also look at the opposite. What if you wanted to send that object away from the Moon and back to the Earth? What would the energy change be? So if that object was moving away from the Moon, it's kind of like moving an electron away from an atom, it needs to gain some energy, some sort of energy. It could come from a collision, could come from a rocket booster. That object moving away from the Moon, it has a higher potential energy. So that's after it's left the Moon. As that object falls onto the Earth, it releases potential energy. But it releases a lot more energy than it gained as it left the Moon. So when that object's back on Earth, its potential energy will be lower than when it was on the Moon. This could be a chemical reaction. The Moon's an atom that has a hold of an electron. The Earth is a different atom and it has a stronger pull for an electron. More energy is released when it falls onto the Earth than it took to remove it from the moon. The net process is that it releases energy. And if this reaction happened in a test tube, it would feel hot. In this chapter of thermodynamics of chemistry, we're really only going to worry about the net change. Future chapters, we're going to look more at the process, and that understanding the process will help us understand rates of reactions too. But energy change. There's some key concepts that we know about. Things like to be in the lowest potential energy state. And that's true whether we're looking at physical objects like planets or chemicals. And just remember, potential energy, chemical energy, it's the same thing. Chemical energy is potential energy, but it's relative to the chemicals we're talking about, and mostly, well, a lot to do with the electrons and their positions about the nucleus. So let's get started with some chemistry concepts. We'll save astronomy and planets and moons for another class. When a chemical reaction occurs, there's really two main things that need to occur in order for this reaction to take place. One of them, energy required for a chemical reaction to start. So what is this energy and what is it used for? One of the easiest ways to visualize this is for reactions in which bonds are broken. So if we had a covalent bond, so we have two atoms in their nuclei with protons, and there's positive protons in there, and there's bonding electrons, and their average distance is somewhere in between the two nuclei. So those atoms, those nuclei, those protons are attracted to those bonding electrons whose average position is somewhere in between the two. If you're going to break a bond, there's different ways to do it, but one way to think about it is the nuclei is going to move away from the bonding electrons. Two things that are attracted to each other, the electrons, the bonding electrons, and the nucleus, are moving away from each other. It's analogous to having a north and a south magnet next to each other. It requires energy to pull the north and south magnets away from each other. If the electrons are moving away from the nucleus, or the nucleus is moving away from the electrons, it requires energy. And that energy can come from different forms. It can come from molecules colliding, so from some collisional energy. It could come from photons being absorbed. There's lots of different ways in which energy could be used to break a bond. In your body, for example, you don't have lots of photons flowing in or electrical energy flowing in. It comes from the collisions. So a good way to look at it, to break a bond is kind of like breaking a bumper bond off your car. It can come from a collision, so some other molecule colliding and knocking with enough collisional energy to knock that nucleus away from the bonding electrons. So, in order for a chemical reaction to occur, we're going to write a few definitions. Reactants must collide with enough collisional energy to break bonds. This is number one. There's a number two that we're going to write on the next page, but we'll go ahead and circle that. And I know that definition doesn't apply to every chemical because some of your reactants you've had so far, it's just been single atoms. In a redox reaction, you could have a nucleus and something losing an electron. We're not breaking a bond if that electron leaves that atom, but it still requires energy. And that energy can come from a collision or it could come from a photon. But to move the electron away from the atom, away from the nucleus, requires energy, just like moving an object away from a planet. And so a statement that's true, energy is required to break bonds, and that energy again can come from different forms, or it requires energy to move an electron away from an atom. And I think that kind of makes sense when you think about pulling a north and a south, pulling those two magnets away from each other. May not make quite as much sense is, it requires energy to move objects that are attracted away from each other. Energy is released when objects that are attracted to each other get closer. And that's just like you walking, you're attracted to the earth and you fall to the earth. You release potential energy when you fall, when you get closer to the earth. When bonds are made, when an atom comes closer to bonding electrons, energy is released. when an electron that was taken away from one atom falls onto another atom, energy is released. So we'll also include that in our statement above. Energy is released when bonds are made or when an electron falls upon an atom. These next two diagrams are showing the net change of chemical energy during a chemical reaction, and you have both types. The y-axis is potential energy, and remember, potential energy and chemical energy are the same thing. So potential energy equals chemical energy. But you have the reactants at a certain potential energy, certain amount of chemical energy. When the reaction is complete and you form all these products, the products are at a lower potential energy. So this would be like you're on the third floor of a building. When you're done, you've produced your product, you're on the second floor. So in this type of reaction, the reactants are losing potential energy, and energy is released. So that energy that's released, well, it could be a photon. So you see when wood burns, different visible photons are coming off. It could make the molecules move faster, so there's heat flowing out. There's lots of different forms of energy, but energy is being released. If you did this reaction in your test tube, this reaction would feel hot. So a good example of this reaction is your natural gas, that combustion reaction that's happening in your furnace, and the heat being released makes the air molecules move faster and warms up your house. Gasoline combustion reaction in your car, that energy that's being released, well, some of it can be used to do work, some of it can go off as heat. Some of it could power your radios for electrical energy. So we'll write that this reaction would feel hot. It also has a special name that you have to memorize. It's called an exothermic reaction. The other type of reaction that happens is where the products have a higher potential energy than the reactants, and that's the one that's shown below. In this case, you have the reactants, the products are produced, they have a higher potential energy. They have more chemical energy. So they gain energy from some source. And a good example would be plants using carbon dioxide and water as the reactants, forming glucose. The plants use the energy from the sun's photons that are striking it, absorb those photons, and use that energy and stored it as potential energy, chemical energy, in the glucose molecules. If this reaction happened in a test tube, it would take energy from the surroundings, which if you touched it would be your finger, and it would feel cold. And since the top one got a special name called exothermic, there must be a special name for the one that would feel cold, and it's called endothermic. Now, as far as the change, and what's the net change? So the exothermic reaction, the reactants are at a certain potential energy, and right now we don't have numbers, we'll eventually have that. But the reactants to the products, that would be the change. And in science, there's a symbol we give for changes, and that's a triangle. Shown there, that's the change in potential energy. So change, a triangle potential energy. For the endothermic reaction, if we were going to label it from reactants to products, there's the change. And if we knew what reaction it was, we could actually give an exact number for the change in potential energy. Also, in one of them, it's losing, the other one's gaining. One of them, the change would be given a negative number, and the other one would be given a positive number. Doesn't mean that energy is negative, nothing to do with that. The negative positive has to do with the process. In the exothermic one, the reactants are losing energy relative to the products. If you lose something, you get a negative. For an exothermic reaction, if the potential energy change was given, it would be a negative number. If you had an endothermic reaction and you're given the change of energy for a reaction, it would be listed as a positive number. So saying that a reaction feels cold means it's endothermic. Saying that the change of potential energy is a positive number means it's endothermic. It all means the same thing.
So, there's a lot of vocabulary on this page. Unfortunately, I have to keep introducing more. Potential energy, it's potential energy. For chemists, it's called chemical energy. There's also another name for it. It's called enthalpy, and we'll see that a little bit later. But enthalpy, there's a letter abbreviation for it, and it's H. So if you see H, that's potential energy. That's the chemical energy. They mean the same thing. So here we have change of potential energy as negative. It could be change of H. If that's a negative energy, that's an exothermic reaction. So down here for endothermic, if the energy was given, the change of H, the change of potential energy would be a positive number. So H means potential energy. You won't see PE, change of PE in any problem. You'll see it written as change of H. So let's write that. Change of potential energy, negative. Change of enthalpy, negative for exothermic. It's a positive number, and we'll eventually give some real numbers for an endothermic reaction. So if we have a reaction that's exothermic, you have reactants that are forming products, and we'll put an arrow like that. The net amount of energy, the net change, is that it's being released. Energy is being, you can think of it as being produced. Sometimes for an endo and exothermic reaction, we put energy, the energy amount, on the reactant side or the product side. For exothermic, since the energy, the net amount is that it's being produced, it would be on the product side. So reactant forming products plus energy. So plus E for energy. If it's an endothermic reaction, you'd have reactants forming products, but the reactants need some energy to form products, so the plus energy would be on this side. So the point being, there's lots of different ways to say that a reaction is exothermic. You can write it as part of the reaction, put energy in there in these two different formats, or you can write a reaction and just give a delta H value. Okay, what else needs to occur in order for a chemical reaction to happen?
Another process that needs to occur for a chemical reaction to happen is illustrated in the example below. This molecule is sucrose, and don't worry, you don't need to have its structure memorized or anything like that. But sucrose is a chemical that's formed from glucose and fructose. These are chemicals we've heard of. There's a carbon ring structure for glucose and a carbon ring structure for fructose, and they get bonded together and form a new molecule called sucrose. And right in here is the connection, bonding connection. So there's an oxygen that's bonded to two carbons in both of the structures. And there we go, we have sucrose. Water can react and break the molecule back into glucose and fructose. So those are the two reactants. Sucrose plus water forms glucose plus fructose. When this reaction occurs, it's this bond that breaks that allows the glucose and fructose to form. So what if, water collided there? Would a reaction happen? What if water collided there? Would a reaction happen? An analogy I like to think of, if you wanted to break your bumper bond off your car, you want to break the bumper off your car. Well, you got to break the bumper bond. So if you want to break your bumper, you want to break that bond, you got to collide with the bumper. In order for this reaction to happen, the water needs to collide with the bond that's going to be broken. Most of the collisions of water with sucrose result in no reaction. So that's another key thing that needs to happen. Yeah, you need to have enough energy to break the bond, but you got to collide in the correct orientation too. So number 2, we'll write it kind of like that. Molecules must collide in the correct orientation. By the way, with another tangent to go off on, if you took sugar and you dissolved it in water, at room temperature, the molecules are moving so slow, at least virtually most of them are moving so slow, that there isn't enough collisional energy to break that bond, even if you collide in the correct orientation. In fact, you could even boil the water, get to 100 degrees Celsius so the molecules are moving faster. But that sugar, that bond that needs to be broken to form glucose and fructose is still relatively strong compared to the molecules that are moving at that higher temperature with a higher velocity, which creates a higher collisional energy. Your body, what's interesting, you can eat sucrose, your body releases something that's called an enzyme, which is a catalyst. But these are chemicals, and one thing that they can do is weaken the bonds. This catalyst that your body makes, it's a protein called sucrase, and it secretes it in your digestive tract when you eat sucrose. And it weakens the bond so much, that when you do eat sucrose, the water moving at 37 degrees Celsius, that's more than enough energy because the bond's so weak to break that bond, to easily break that bond. Next quarter, when we learn about reaction rates, anything that can make a reaction happen easier, faster, requires less energy, will affect how quickly reactions happen. Catalysts, temperature, things that we're understanding right now a little bit, well, those are going to be variables that we can use to affect the rate of a reaction. But for right now, the two things I want you to know is that chemicals, in order for a reaction to occur, chemicals must collide with enough energy to break some bonds, and equally as important is that they must collide in the correct orientation. One last concept to keep in mind as we talk about energy and energy requirements for a chemical reaction is our velocity profile that we introduce for gases. We can calculate the average velocity for gases, but again, the fact that there's a velocity distribution, this is true whether you're a gas, liquid, or a solid. And if energy is required to break a bond from collisions, which molecules are involved, which ones have enough energy to break a bond? Are the ones that are moving slow or the ones that are moving fast? It's these molecules that are moving really fast, those are the ones that have enough energy to break the bonds. And if we increase the temperature and redrew our velocity profile, it's going to be skewed more to the right, and there's going to be more molecules that are moving faster. As you increase temperature, there's going to be a higher fractional amount, a higher number of molecules that have enough energy to break the bonds. That makes it easier for the chemical reaction to happen. We'll see in the laboratory, and we've talked about this before, but temperature is a variable that can affect reaction rate. And we'll use it all the time this year to do that. As I mentioned earlier, thermodynamics, that field of study, looks at the energy changes that happens during a process. If we're a chemist, for a chemical reaction, it's thermochemistry. As far as energy in units, the SI recommended unit we're going to use most of the time is joules. And the fundamental units of joules is kilograms meter squared per second squared. Joules can be abbreviated as a J. Now, you've heard of lots of different energy units in your life, your experience. Food labels, the classic one. The unit on there is calories, and there's a relationship between joules and calories. But that calories, that's a nutritionalist calories. I'm going to give you a relationship, and somehow we're going to get to that nutritionalist calorie. So a nutritionalist, instead of having to say kilocalories, before our American society embraced prefixes, they came up with just the uppercase calories. So on your food label, it says approximately how many calories do you metabolize every day. Depending on your weight, but it's approximately 2,500 calories per day, and the uppercase calorie. As far as in terms of joules, how many joules do you metabolize per day? You metabolize and you produce about 10 million joules worth of energy every day from the breakdown of your fuel molecules. So this is how much heat radiates from your body. Or in terms of kilojoules, it's about 10,000 kilojoules per day. So kilojoules, kilocalories, and the nutritionalists went with the uppercase calories. It's a little bit easier to say. Okay, as far as energy, there's really two broad classifications. That's potential energy and kinetic energy. We'll talk about both more on the next page. But as far as subclasses of those, there's lots of different types that you've heard about. Some we've actually talked about. So one of them would be chemical energy, and it's a form of potential energy, but just as far as different types, chemical energy is a type. And again, that we've made this discussion before, but that chemical energy, that's the sum of all the potential energies of the electrons to the nuclei that are part of that structure. And there's some other aspects of attractions that go into it too, but for all we know right now are electrons in the nuclei. So that's chemical energy. It's a form of potential energy. Whenever you have two objects that are attracted to each other, there's potential energy. Another type would be thermal energy. This is motion energy. But heat, thermal energy. This thermal energy comes from matter, chemical substances moving around, which is a motion energy, kinetic energy. Another type is radiant energy. So this, what falls under that classification, like the photons of light that you see. These are tiny, tiny little particles called photons. You've heard of X-rays, UV, infrared, microwaves. These are tiny little particles, and they're all radiant energy. Then some other potential energies like gravitational potential energy. Again, you have a certain potential energy sitting on the third floor in the laboratory of this building. Your potential energy is different. You've lost some massive energy when you've gone down to massive potential energy when you've gone down to the second floor. Another type of attraction that's different than the electrostatic attraction that causes chemical energy, that's different than the potential energy caused by gravitational forces, is nuclear energy. And we'll learn about that next quarter when we talk about the structure of the nucleus and nuclear reactions. But the nuclear force, there's an attraction between the neutrons and the protons. And that potential energy that exists depends upon the strength of that attraction and how close they are. Another type of energy that you could classify as electricity, the electrons flowing. Okay, so the electrons are moving. Is that potential energy or is that kinetic energy? Kinetic energy, everything's moving, so you got kinetic energy, but what's it being used for? If those electrons are falling onto another atom, it's losing some potential energy. So yeah, they're moving, but when an electron goes from one atom to another, like an electron flowing into a wire, the electron doesn't slow down when it goes from one atom to another, but it loses some potential energy when it falls and orbits a new atom. Another type is work. Work is energy. Work is the amount of energy to move an object in a field. So you have a gallon of gasoline, you can harness that chemical energy, and some of that energy can go off as heat, thermal energy, and some of it can be used to make your car wheels go round and round to do some work. So work is the energy required to move an object in a field. Another form of energy could be sound. Sound is the movement of molecules. Sound can travel through air, so it's the movement of those air molecules that can travel through an object, a solid object. Those molecules that are part of the solid object, they're not free to move completely like a gas molecule, but they do move. They're a little bit restricted, but they vibrate with a certain motion. So sound energy, that's a form of kinetic energy, but we'll just list sound. We could keep going and going with some different examples, but maybe one last one would be like a spring. When you can store some potential energy by how you compress or expand a spring into a certain position. But that's a form of potential energy. Lots of different forms of energy, two basic types, kinetic and potential, but spring. One last note I forgot to mention as far as units of energies. Sometimes you could just say joules. Here's how much energy there is there. Sometimes we give the energy a little bit more relative, like we do on a food label. Like there's 100 calories worth of chemical energy, fuel energy in a piece of bread. Or how much energy is there in a gallon of gasoline. So what you might see for our chemical reactions, instead of just joules, you might have it, and you will have it in this chapter, how many joules per mole of reactant that may go through a reaction. We could do that for your natural gas burning. If you have this much natural gas, how much energy per mole could it produce? You'll see the energy made relative by putting it per mole. As far as the two major categories of energy, one of them is kinetic energy, the other is potential energy. Kinetic energy is the energy of motion, of movement, and the equation is kinetic energy equals 1/2 mass times velocity squared. 1/2 mass times velocity squared. If we want units of joules, that mass quantity needs to be in kilograms, and the velocity needs to be meters per second. The SI unit of joules is kilograms meter squared per second squared, so that tells us what units our variable should be in. Potential energy, we're not going to do any calculations with it, but we do know a few concepts of it. The equation for gravitational potential energy is mass times the gravitational constant times h. We could also do some calculations with electrostatic interactions with the electron and the proton, but that kind of gets complicated. That's something you'll save for graduate school like I did. By the way, just electrostatic potential energy, the potential energy of an electron, it's related to its attraction to the nucleus, but it does get a little more complicated. Potential energy is for that electron depends upon its attraction to the nucleus. So if you had a nucleus that's positive and you had some negative electron moving around, there's an attraction. It gets complicated because that electron is moving randomly and it doesn't have a fixed position, so that can get it complicated. The other thing that can start to make things complicated, you also have to worry about other electrons. I mean, you have a certain potential energy, but what if you were repelled by other objects? You're attracted to the Earth, and there's a certain potential energy, because of that, but you really don't have to worry about any other interaction with other objects, like a person sitting next to you. But electrons do. If there was just one electron and it had an attraction to this nucleus, in this example, it has a certain potential energy. But what if another electron went flying by and it got in between it? That position causes some repulsion. That repulsion is part of the calculation for potential energy. This can get pretty complicated. Well, what if it got a little more complicated? What if there were some bonding atoms and there were some nearby planets? Well, now we still have that attraction there, but now we have that attraction over there. It can start to get really complicated when you try and model this and do calculations. But we'll save that. We'll see next quarter, we'll look at some of the analysis of the theory that analyzes the movement of electrons within a chemical, and the analysis that shows potential energy calculations. It can get pretty complicated. The last category of energy on this page is internal energy, and it's not a separate form of energy like kinetic energy, potential energy, but it has to do with more of the system. What types of materials are part of your system. So let's, we're chemists, so we're going to think about it in those terms. So if you had a beaker of reactants and was sitting on your laboratory bench, well, those chemicals, those reactants, they're moving around, so they have their own kinetic energy there, but they're also part of this room that you're in with your beaker in the laboratory room, and the Earth's moving, so there's the Earth, well, it's moving in the solar system, so there's that kinetic energy. Which kinetic energy are we going to use when we look at the chemical reaction? Well, the internal energy, it's the energy that's associated with, just for a chemist, for the chemicals that are part of the reaction. We don't need to worry about how fast the Earth is moving. That beaker sitting on your laboratory bench, there's a certain potential energy. Well, if you're on the third floor in our chemistry lab, there's a certain potential energy with the Earth. It's a little bit different when it's on the second floor of our building. Do we take into account that potential energy? And is that part of the chemical energy? No, you just worry, when you have a chemical reaction, you worry about the chemical reaction. You're going to have the same reaction on the third floor as the second floor. So that beaker of reactants, there's some total energy, And part of that internal energy is the internal energy. So total energy, internal energy. And by the way, internal energy can be abbreviated as U, the letter U. So total energy is U plus, all that extra energy of the beaker being on the third floor, the second floor, energy potential that's, beyond our system. So we'll write that in there. Energy potential plus the fact, it's part of the earth and it's moving, there's some energy that's kinetic. When we look at chemical reactions, we ignore this part. So chemists ignore that and we just pay attention to what's happening to the chemicals that are part of the reaction, and that's internal energy. The internal energy is the energy of the chemical substances that are part of the reaction, and that would include their kinetic energy and their chemical energy. So that U, that internal energy, that would equal the kinetic energy of the reactants and the products that are involved, plus the chemical energy. By the way, that kinetic energy of those molecules in your beaker, that depends upon a certain variable. The kinetic energy depends upon the temperature. Temperature is a reflection of how fast they're moving. So as temperature changes, it means the velocity of the molecules is changing, which causes a change in the kinetic energy. So if we're going to put in, it depends upon T, temperature. Chemical energy, the potential energy of the chemicals that are involved in the reaction, potential energy is related to attractions. And the chemical bonds, if you have molecules that have bonds, the attraction between the bonding electrons and the positive protons in the nucleus. That's part of the potential energy. Also, something that we'll learn about later, potential energy between molecules. We'll learn that molecules are attracted to each other, and we'll learn the different types of attractions. It's still electrostatic. Chemicals are made of electrons and protons, but there's attractions between molecules. So the potential energy of our reactants, well, there's attractions that you need to consider when you look at the change, when you look at the internal energy of a system. Okay, so here's an embedded practice problem. Go ahead and pause the video, read the question, unpause, and we'll see if you're on the right track in your goal to solve this problem. What are we trying to solve? We're trying to solve for the kinetic energy. So we'll use the kinetic energy equation, which again is in your information packet. So in order to get kinetic energy, we need mass and we need velocity. If we want to express it in SI units, in terms of joules, the mass needs to be kilograms and the velocity needs to be meters per second, so that we get kilograms meters squared per second squared. So as we read through the problem, the question wants to know kinetic energy, but the kinetic energy of one single atom. And it's for a helium atom. And here's the average mass of a helium atom. That needs to be converted into kilograms. As far as the velocity, we have helium and we have the average mass. How can we get velocity? Well, we know what temperature it is, and we know what the chemical is. And that's all you need to get the average velocity. So use the equation that allows you to calculate the average velocity given the temperature and the chemical of interest. So pause the video, get the average velocity, and get that mass in terms of kilograms. So the first step, converting 4 AMU into kilograms, 4.002602 AMU, using the relationship between grams and AMU, and the relationship between kilograms and grams, we get the mass of one atom with a unit of kilogram. The mass is a tiny, tiny mass, around 6.6 times 10 to the negative 27th kilograms. And we'll plug that mass into our kinetic equation down below. As far as velocity, the average velocity for a helium atom at that temperature is a little more than 1,363 meters per second. And we'll plug that velocity into our kinetic energy equation. And when that's squared, that'll give us meters squared per second squared times the mass in kilograms. That'll give us a unit of joule. And that kinetic energy is approximately 6.17 times 10 to the negative 21 joules, or kilogram meter squared per second squared. And just remember, not that you have to have this memorized, but when you metabolize and all those fuel molecules and you release energy, you release about 10 million joules worth of energy per day. But this is the kinetic energy of just one helium atom. And it's 6.17 times 10 to the negative 21 joules. And what exactly does that mean? This means that if this helium atom moving at this speed with that mass, if it collided and lost all of its kinetic energy, so it had zero velocity, that's the energy that could be harnessed. That's the kinetic energy it could give to some other object. There's a relationship between temperature and heat. But what exactly is heat and what does temperature tell us again? Remember, temperature, the measurement of a temperature, it's based upon the average speed of a substance. But what is heat? Heat is actually a change of energy. It's how much energy flows into or out of a piece of matter. Heat is often given a letter abbreviation, and the letter is Q. Sometimes it's uppercase Q, sometimes it's lowercase q. In this class, for the textbook that we're using, heat will be designated by lowercase q. So, how do you get heat and how's that related to temperature? And let me give an analogy. Say you had a cup of water and the water's at 100 degrees Fahrenheit, and you had a bathtub full of water and its temperature of the water is also 100 degrees Fahrenheit. What if both cooled to room temperature, around 70 degrees Fahrenheit? They're both at the same temperature, you both have this, the same temperature change, but how much energy flowed out? Well, it depends upon how much mass of water. Most of us understand there's more of an energy transfer, more heat loss from the bigger mass of water that's coming from your bathtub. Or another way, what if you had a pot of water? How much energy do you have to add so that that pot of water boils? How much heat has to flow in? Heat is how much energy flows in or flows out. If you had a small pot of water, it doesn't require as much heat to reach the boiling point for that temperature change versus a really large pot of water where you're cooking that corn. So there's a relationship between heat and temperature. Temperature is not energy, but it's a reflection of the average velocity. So what exactly is this relationship? What are these equations that can give us this information? Well, one thing should be somewhat obvious is that the heat or the energy that flows into or out of a system, how much needs to go in or go out, depends upon what temperature change you want to occur. So this Q is based upon the temperature change. So we start seeing this relationship develop here. And by the way, a triangle in our equations and in most science equations, that means change. And a change of temperature, whenever you have a change, it's always final minus initial. So that triangle in T, that's temperature final minus temperature initial. The other part of this relationship is actually a constant. And this constant is called heat capacity. And it's given the letter abbreviation of C. So here's an equation, and we'll explain what heat capacity means in a second. But the heat flow equals the change of temperature times a constant C, which is called heat capacity. This is one equation for heat. And what exactly is heat capacity? Well, it's a constant for an object, and it's an object that's always the same. And a good analogy is if you had a pot of water on your stove, and in this pot, whenever you're going to boil this water, it's always the same amount of water in this pot. How much energy would be required to cause this pot of water to boil? Let's say you always put 2 quarts of water in there. If you always start at the same temperature, the amount of energy that needs to go in, how many joules worth of energy to get it to that boiling point for that fixed amount of water that's always in there should be the same. So heat capacity is a constant for an object, and that object always has the same mass, everything's the same with it. So if we were doing a study in our chemistry lab, if we had something that we were using to monitor temperature changes as heat flowed in, we would get this object and determine what this constant is for that specific object. That's heat capacity. The units for this constant are joules per degree Celsius, or joules per temperature change, but the ones we'll use are joules per degrees Celsius. So if temperature change was in Celsius, and we plugged change of temperature and this constant in there, that would leave us with units of joules. And heat, Q, that's energy. It should have energy units. Q can also be expressed in a slightly different equation, and the constant is slightly different. So instead of a constant of heat capacity, it's a constant that's called specific heat, and the letter abbreviation for it is S. And specific heat, this constant is specific for a substance instead of just some object, some device. It's for a substance. So water would have a certain specific heat. A different type of metal like aluminum would have a different specific heat. And this constant is determined for each substance. It has certain units, and the units are joules per gram per degrees Celsius. What exactly do those units mean? The way you get this constant is you take 1 gram of substance and you figure out how many joules worth of energy is required to heat the substance 1 degree Celsius. If we look on the next slide, here's a table that's also in your information packet of specific heats for a variety of different substances. One of them being water. And that value for water in its units is 4.18, and the units are joules per gram per degree Celsius. And what this says that it takes 4.18 joules worth of energy to heat 1 gram of water up 1 degree Celsius. If we looked at something like aluminum, its value is a little different. 1 gram of aluminum would require 0.9 joules worth of energy to heat it up 1 degree Celsius. Why would they be different? Well, heating things up, it's more than just moving in 3 dimensions. How these bonds and things can vibrate and move. The energy of movement can also be incorporated into just the vibrational energy or the bending of the molecule. So there's different numbers for different substances. The equation using this constant is slightly different than the one up above with heat capacity, but the Q equals this specific heat, this constant, still using the change of temperature, but in this one you also include the variable mass, so M for mass. So where would you use this equation? Well, if you wanted to find out the heat flow for a temperature change, say the temperature change from your cup of water or bathtub full of water going down to room temperature, what would be the heat flow? Well, you have to include the mass. And when you include that mass and with that temperature change, obviously it's going to be a lot greater of a heat flow if there's a bigger bathtub full of water of mass versus a cup of water of mass. So this equation seems to make sense. But this specific heat, it's a constant for a substance. And in one of our upcoming laboratories, we're going to look at some different metals and experimentally determine what the specific heat is for a metal. As far as these equations and how they're written in your information packet, so here's Q using heat capacity with C, and there's the heat flow using specific heat. Note that the change of temperature, again, it's always final minus initial. Sometimes this Q can be negative and sometimes it can be positive. And it's not that you have a negative or positive energy, it's the fact that that negative or positive tells you which way the energy is flowing. Is it flowing into your piece of material or is it flowing out? If something loses something, whether it's energy or money, if you lose something, then negative should be your answer. If something's gaining something, then that change should be a positive number. So it's real important when we determine Q's whether it's positive or negative. So when you determine Q, sometimes it's positive, sometimes it's negative. One of them means that it gains energy, the other one loses energy. So here are Q values, negative or positive. One of them is gaining energy, one of them means that the piece of matter is losing energy. Pause the video and draw a line to end it, from gains energy. Does that go, are you going to draw the line up to there, or are you going to do it down to there? So pause the video and indicate when Q is positive or negative what it means for that piece of mass. If something's positive, it means it's gaining something. So if the heat you calculate is positive, it means it's gaining energy. If Q is negative, it means it's losing energy. If something's gaining energy, it'd be like your pot of water gaining energy from your stovetop. The temperature would increase. So if Q is positive, it means that final temperature, is increasing. Make sure things make sense. So Q is positive means temperature is increasing. If Q is negative for a substance, like your bathtub full of water going from 100 degrees Fahrenheit down to room temperature, it's losing energy, losing kinetic energy. That Q value that you calculate should be negative, and it means that final temperature is decreasing. So the final temperature decreases. If Q is negative, it means the average speed of those molecules is slowing down. If Q is positive, like your pot of water, those molecules are moving faster near the boiling point than when they were at room temperature when you started heating it. So here's a practice problem. Go ahead and use the heat equation and determine that value given the information above. So go ahead and pause the video, unpause when you're ready to check your answer. In the problem, you weren't given the heat capacity, but you were given the mass of the sample, and the sample's water. So as far as what heat value, what heat equation you should use, you should have chose the one with specific heat. When you look at the problem, temperature's increasing. So when we do calculate the heat value, that water must be gaining energy, so that Q value should be positive. So we have a constant and it has units. Again, the units tell you, the units of your constant tell you what units your variable should be in. So make sure your amount of substance, the mass, is in grams and the temperature change is in Celsius. The change of temperature is always final minus initial. The final temperature is 50 degrees Celsius. So the change of temperature is a positive 30 degrees Celsius. As far as canceling units, grams and grams cancels, and Celsius cancels. and we're left with a unit of joules. And our answer is around 2,000 joules, 1.88 times 10 to the third joules. Heat is the flow of energy from one object to another, but energy can have lots of different forms. But when we typically look at heat and that flow of energy in our everyday lives or in our laboratories, those experiments we're going to conduct, what is the energy flow? And a good example that you observed before, what if you had a hot cup of tea or a hot cup of coffee and you let it sit on your counter in your kitchen at home? Eventually, that temperature of your substance, that coffee or tea, is the same as the room temperature. So the temperature decreased, which means the kinetic energy of your liquid mixture decreased. So the heat flow that we see is the flow of kinetic energy from one substance to another. And you already know this just from your observations and paying attention to life. The energy flow, that kinetic energy flow, that heat flow that we observe most often, the energy flows from high temperature to a region to an object of lower temperature. And eventually, given enough time and the ability to conduct this heat, the temperatures become equal. So what exactly does that mean? I mean, what's the physical, what's the chemical picture of what's going on? And shown below is a diagram that, we could envision. What if we had a substance in two different containers? And we'll just, we could make it any substance, but let's just say it's O2, and then it's O2 on both sides. But initially, the temperature is different on both sides of the container. So let's say on one side, the initial velocity was 400 meters per second on the left-hand side and 600 meters per second on the right-hand side. So those are the average velocities. On one side, the temperature is higher. And on one side, when the oxygen molecules, when they collide with the container initially, one of them has a higher collisional energy. So from both of those, draw an arrow to what side of the container would have a higher temperature and which one would have a higher collisional energy when these molecules collide with the interior surface of the container. So if the average speed is higher on the right-hand side, it means that it has a higher temperature. The faster something's moving, when it does collide, it would have a higher collisional energy. I mean, you worry more about crashing at 60 miles per hour than you would if you're only traveling 5 miles per hour in your car. So on the right-hand side, for both of them, it's higher. Let's just say that the walls of the container, only on one side is heat allowed to conduct. And that's the middle portion. So this portion, this wall of this container can conduct heat. On the other sides, it cannot. So what exactly does it mean that it can conduct heat? When you have these molecules moving around, and on both sides they move around and collide, but it's happening in both directions. When those oxygen molecules collide with that material, with that surface wall, what can happen? Well, like any collision, there can be a transfer of kinetic energy. So maybe those oxygen molecules collide, lose a little bit of their kinetic energy, and that wall material can move with a higher velocity. And since it's a solid, vibrate with a higher velocity, so there's more kinetic energy in that solid. And that vibrational energy can transfer through the material and go to the other side. And when the molecules on the other side collide, maybe that can be transferred. You have collisions on both sides of that wall. Both sides, the oxygen molecules can lose kinetic energy in a collision, and on both sides they could actually take kinetic energy from a collision with the wall material. But what do you have on the right-hand side, where the velocities are greater, well, it's a higher collisional energy. You have a higher collisional frequency too. You're having a transfer of kinetic energy in both directions, but with a side that has higher velocity, you have more movement. You have the net movement, so net movement of kinetic energy to the side where it's lower velocities, lower collisional energy. And eventually, because of these random collisions, you'll have a homogeneous transfer of energy from one side to the other. It doesn't mean molecules stop colliding, but the net is the transfer of energy, transfer of heat from one side to the other. Well, that the net transfer is zero when the temperatures on both sides are the same, when the velocities of the oxygen molecules are the same. And this is exactly the same thing that happens to your cup of coffee and the water molecules and the air molecules that surround your cup of coffee. And again, if there's a temperature difference between two objects, the net flow of energy, the net flow of kinetic energy, the net flow of heat is from a side of higher temperature to the side of lower temperature, from the side of higher velocity to the side of lower velocity. And you reach some sort of equilibrium when the net flow of energy is zero, when the temperatures are the same on both sides, when the average velocities are the same on both sides. So we can tag a little bit more on to this statement. For our example below, where it's the same substance on both sides, the same oxygen molecules, the average velocity would be the same. If it's different substances like air and water in your cup, the average kinetic energy would be the same. The temperature would be the same. And again, the process doesn't stop. The collisions don't stop, but the net flow of energy is zero. Shown on this page is another example problem, embedded practice problem. Go ahead and pause the video, decide what equation you're going to use, unpause the video when you're ready to solve the problem. So, you need to figure out how much heat, so that means we need to solve for Q. Which Q equation? Well, we're given the amount of substance, so you'll want to use the Q that has mass in the equation. We're also dealing with water, so you want to use the specific heat that's specific for water. So we need the mass of water in this 100-gallon water heater, and we need the temperature change. So what units? Well, again, the constant tells us what units each one needs to be in. The amount of water needs to be in terms of grams, and the temperature change needs to be in degrees Celsius, not Fahrenheit. That would give you two different changes of temperature. So it needs to be in degrees Celsius. So what's the mass of 100 gallons of water? Well, density gives you the relationship between volume and mass. The density that's given to you in the problem is grams per milliliter. So the first step in the process was to convert 100 gallons into milliliters. That's the first two conversion factors that are shown here. And then the next step is to use the density relationship. This mass amount of water, which is 100 gallons of water, is around 356,000 grams, 356,967 grams of water. That needs to change 10 degrees Fahrenheit. The next step is to convert our temperatures from Fahrenheit into Celsius. The final temperature is 130 degrees Fahrenheit, so that's our T sub F. And converting that into Celsius, that temperature is around 54 degrees Celsius. And we'll give it more than two significant figures, 54.44 degrees Celsius. The initial temperature, the initial 120 degrees Fahrenheit, is around 49 degrees Celsius. 48.89 degrees Celsius. And you can tell, That change of temperature in Celsius is quite a bit different than Fahrenheit. It's important to be in the correct units. But after doing our calculation, how much energy, what would the heat flow have to be to heat 100 gallons 10 degrees Fahrenheit? And it's almost, it's a little more than 8 million joules. 8,281,279 joules. And just to give you some sort of perspective, what does that mean, 8 million joules? Well, again, not that you deal with joules every day, but if you metabolized all your fuel molecules and all you did was sit around, how much energy would you release? How much heat would flow from your body? Around 10 million joules per day. So if you could collect all the body heat, all the kinetic energy flowing from your body, you could heat that hot water heater one time. Okay, so what about this graph up above, and what does it mean? This is showing the temperature change as heat is added. And you get this sort of plot with any substance, but this one's in particular for pure water. So the x-axis, heat added, and what's the temperature change of the water? If you started with solid water, so we're below 0 degrees Celsius, so starting down here, if you took an ice cube from your freezer, and your freezer temperature is way below 0 degrees Celsius, but if you start heating it, and that water, that solid water, absorbs some kinetic energy, some heat energy, the temperature of the ice would start increasing. So heat added, starting there, it increases, and then it plateaus. And what's happening there? That's the temperature, under normal conditions when water starts melting. And that melting point, also called the freezing point, we'll abbreviate as MP, melting point. And as you add heat, once you reach the melting point, the temperature doesn't change. So what does that mean? It means when you have a substance melting, this goes beyond just water, for any substance, when you're at the temperature where it's melting and you keep adding heat, the temperature remains constant. So if you had a styrofoam cup full of water and there's ice in there, during that time in which the ice is melting, the temperature of your mixture, or of ice and liquid water, that temperature would remain constant until everything's melted, and then you have liquid water, and once you reach that point, here, as you have liquid water and you add heat, the temperature increases. So if you have your pot of water at home and you turn on the burner, that liquid water, as you add heat, the temperature increases, and then all of a sudden it plateaus again up here. What's happening there? You're having a phase change. This is the boiling point, which we'll abbreviate as BP. As that water, or this would be true for any substance, as it boils, the temperature remains constant for the whole process until all of it becomes a gas. Once all of it becomes a gas and you have just gaseous substance, as you add heat, temperature increases. So what does this say about this phase change? If you have water, and say you have a pot of water and it's boiling, that temperature of that liquid remains constant until all the liquid becomes a gas. This is pretty interesting, and we'll see it experimentally when we're in the lab. And for my lab, my household, my kitchen is also my lab. How does this impact us when we cook at home? Maybe you're making your turkey or your chicken and you're cooking it in the oven. If there's still water in that pot, that food is going to cook at that boiling point temperature. And so when you're cooking your chicken or your turkey, maybe you have it sealed, as long as there's water, that's the temperature which the food cooks. When do you start seeing the chicken or something burn? Well, that's when all the water evaporates and the temperature increases, and then the oxygen molecules can collide with at a high, moving faster at a higher temperature, and you start forming that black stuff. It's when all the water's gone, the food cooks at a higher temperature, that you start burning your food. By the way, going the reverse direction, taking away heat, going from a liquid to a solid, so the freezing point, melting point is the same temperature, but if you had liquid water that was freezing and becoming a solid, it freezes all at the same temperature. If there's water and solid ice in there, till all that liquid becomes a solid, that temperature would remain constant as you take away heat. So all this information that we're providing, it's given you valuable tools, conversational tools to talk about when you're preparing that special meal, like Thanksgiving or some birthday meal. You can talk about cooking and phase changes. And during the winter, you can talk about melting of snow or the freezing of snow. When chemists study the energy of a chemical reaction, again, we study the internal energy. What's the energy of the reactants and products? That's our system. Often studying the energy of a chemical reaction, so that's thermodynamics, a goal of the study is to look at the chemical energy of the species that are involved in the reaction, so the reactants and products. As explained earlier, there are two types of chemical reactions. There's exothermic and endothermic. For exothermic, the reactants form products, and in the net process, energy is released to the surroundings. This energy can take on a lot of different forms. For example, for gasoline, a combustion reaction with gasoline, you could just burn gasoline and there's lots of heat being released. So the kinetic energy of the surrounding molecules is greater, they're moving faster. You could see photons coming off, so the visible light that you see from a combustion reaction. Or that energy could be used to do work, like make your wheels go round and round if that reaction was happening in your engine. Regardless, there's energy being released. The energy can take on lots of different forms, but the total amount of energy from a gallon of gasoline, if it goes through a combustion reaction, it's constant. So as far as energy, we could say, different forms. It could be radiant, kinetic energy, photons, work, lots of different types. For endothermic reactions, the reactants are taking energy from the surroundings. So in the net energy change, energy is flowing into the system. So we could write our chemical reaction with the reactants having the energy on that side of the equation. Regardless if it's exothermic or endothermic, what's definitely true comes from the law of conservation of energy. Energy isn't created or destroyed during a chemical reaction. Its form may be different. It can be transferred or transformed. The question that chemists really want to answer is the flow of energy into the system, or is the flow of energy going out of the system? So when chemists study thermodynamics, they're really looking at that flow of energy. So reactants have a certain amount of internal energy, the products have a certain amount of internal energy. So we could make a diagram U, that's the internal energy, and the reactants would be at some internal energy level, so reactants. If the flow of energy is going into the reactants, well then the products would have a higher internal energy. If this is the case, then from reactants to products, that's our change of internal energy. And in this case, that change would be a positive number, meaning energy would have to be flowing into the system, into the reactants, to make the products at a higher internal energy. If you had the opposite type, where the products were at a lower internal energy, so from reactants to products, that's our change of U, and in this case, that U would be a negative number, meaning that energy is flowing out. And again, that energy could be in different forms, but it's flowing out to the surroundings. Also remember what we said earlier, internal energy, it's the kinetic energy and potential energy, and for chemists, of the system, of the reactants and products. And it's nice to know exactly what the internal energy is, but knowing what the change is of internal energy for chemists, that provides a lot of information. So when chemists look at thermodynamics and studies, we often look at what's the change when reactants form products. So the change of internal energy equals the change of kinetic energy plus the change of potential energy. And remember, if we set up an experiment where the temperature is constant, then the change of kinetic energy equals 0. So if we were measuring energy changes from a chemical reaction and temperature remains constant, well, that change of energy would be directly related to the change of potential energy. And again, potential energies are attractions, and those attractions could be protons, the nucleus that has the protons, and the attraction to bonding electrons, which is electrostatic potential energy. It could also be attractions that occur between molecules. So measuring the energy change can give you an idea of the chemical energy. What's the chemical energy difference between the reactants and products if we run it at constant temperature? Some of our experiments we're going to be doing, we're going to run it at constant temperature, and we're going to do chemical reactions and somehow collect all the energy, all that heat energy that's released from a chemical reaction, collect it, measure it. Somehow we're collecting all the energy from a reaction, and all that energy we're collecting that we're going to be able to somehow measure, well, that's the change of chemical energy. We'll see it, and we'll discuss it in a few slides a little bit later, but when we do our chemical reaction, and it's going to be an exothermic type where energy is released, water molecules are going to be surrounding the reactants and product, and the water is going to collect the energy, collect that heat that's coming off of the reactants and products, and from that piece of information we should be able to get the potential energy change, which is the same thing as the change of chemical energy, which is the same thing as the change of internal energy. But we'll see that and discuss it and describe the experimental setup a little bit later in about 10 slides. With all this information about internal energy, let's put our minds to a test. What if we had a reaction vessel that was thermally isolated, so there was no energy transfer to the surroundings? Inside our box are the reactants, and outside the box is the surroundings. So no energy transfer, that means Q would equal 0. It means there's no heat flow from the system molecules, the reactants and products, to the surroundings. Let's give some sort of generic letter for our reactants. Let's say our reactants were A molecules, so just A, and these A molecules formed B molecules. So there's a bunch of A molecules in our box, moving around, colliding, and what if we had a chemical reaction and we formed B molecules? So there's two different scenarios. Energy was either released or energy is taken in. So exothermic or endothermic. You should be able to fill in these two blanks, reading what the little paragraph is telling you. So pause the video and fill in those blanks. It's either going to be increase, decrease, or maybe remains constant. So pause the video, unpause when you're ready to check the answer. In the first example, if the chemical energy is harnessed from the reactants, meaning the B products are at a lower potential energy, well, that potential energy, that chemical energy, needs to go somewhere, and it becomes the kinetic energy with the products, meaning the product molecules, the B molecules, their speed would increase. We're not creating or destroying energy, the first law of thermodynamics, So that chemical energy, that potential energy of the reactants, if the products are lower, then that energy must go somewhere, and it goes to the kinetic energy of the products. And it's the opposite. If the products have a higher potential energy than the reactants, well, how did they gain energy? How did they gain potential energy? That massive energy must come from somewhere, and it's coming from the kinetic energy. So if those product molecules, those B ones, have more potential energy, and you take it from the kinetic energy, meaning the product molecules would be moving slower. Note that our examples experimentally, when we conduct the labs, we're not going to be isolated from the surrounding molecules. But the same sort of energy flow could happen, the transfer of kinetic energy to potential energy, or vice versa. Instead of being isolated between the system, that chemical energy from loss from the reactants could flow out to the surroundings, meaning the surrounding molecules could move faster if the system molecules lost some chemical energy. Vice versa, the surrounding molecules could lose some of their kinetic energy and give it as potential energy for the system molecules. Hopefully you're getting all this system surroundings verbiage down. There's a lot, but you just have to keep practicing, and we'll keep practicing on upcoming pages. Thermodynamics is the study of energy, and there's lots and lots of different fields for thermodynamics. For chemists, we study the reactants and products. When you have thermodynamics, they often call the objects, the samples you're studying, the system. So what is the system for chemists? It's the chemicals that are part of the reaction. So what we call the system are the reactants and products. Everything that's around the chemical reaction is called the surroundings. So let's look at a typical reaction vessel in our laboratory. So here's an Erlenmeyer flask. And let's just say we're doing an aqueous reaction, and the reaction is zinc nitrate reacting with magnesium. This is something that you did this quarter, a redox reaction. So there's the reaction. Every atom, every chemical that's part of the reaction is the system. Any other molecule is called the surroundings. So if we looked at this diagram, and I asked you to label the system and the surrounding objects or chemicals, you should be able to. So pause the video and look at the chemical reaction and look at everything that's in that picture, and under the system, write for each chemical that's part of the system, write it down, and everything you think that's part of the surroundings, write it down. Unpause the video when you're ready to check your answer. For this aqueous base reaction, there are 5 different chemicals. Nitrate's a spectator ion, even though it's on both sides, you don't need to write it once. But zinc the cation, elemental zinc, magnesium the cation, and elemental magnesium. As far as the surroundings, well, the water is the medium in which the reaction's occurring. It's part of the surroundings. The glassware, that Erlenmeyer flask, that's part of the surroundings. The air that's moving around, that's part of the surroundings that we can see from this picture. I'm not sure if this reaction is exothermic or endothermic, but it's one of the two, and if the energy flow was from the system to the surroundings, then the water molecules could gain some kinetic energy from the heat transfer from the chemical energy from the reactants, and that could be transferred to the air molecules that collide with the water when the water molecules collide with the glass, or if your finger was touching the glass, it could be transferred to there. Vice versa, if this was an endothermic reaction and the flow of energy is into the system, where does that energy come from? Well, from a system like this, it'd have to come from the kinetic energy of the surrounding molecules, like the water. And if that was happening, then the water molecules would move slower because they're losing kinetic energy, because that's becoming potential energy in the products. By the way, our one laboratory we're going to be doing, it's going to be an aqueous-base reaction, kind of like this, except it's going to be an acid-base reaction when we do it in the laboratory. The water is going to be part of the surroundings. And somehow that water, it's either going to give up some kinetic energy or its kinetic energy is going to be decreasing. But it's the water that we're going to be looking at and looking at its temperature change. But one of the most important things to take from the slides is their system and their surroundings. The reactants and products are part of the system, and only them. If the reaction is aqueous-base, then water is part of the surroundings. Even though it's kind of mixed in there with reactants and products, it's part of the surroundings. And also, if it's an aqueous solution, even if water was a reactant or product, water is the medium which it's occurring in. Most of the water molecules aren't involved in the reaction, and the water's still considered part of the surroundings. And that'll be the case for all of our examples this quarter. So remember, heat is the flow of energy. So it's when you look at the heat, it's a change that occurs. So if we look at the heat of a reaction, that heat flow, is the heat flowing into the system or is it flowing out of the system? Heat, as we mentioned earlier, it can be given by the letter Q, uppercase, lowercase. Sometimes for this chapter, for this textbook, it's lowercase. But Q is the heat flow, and we want to be a little specific when we talk about Q. Are we talking about Q of our system? Is the energy flowing into our system, or is it flowing out? The analogy, if you had a cup of coffee, if the coffee is your system, and it was boiling close to the boiling point of water for your cup of coffee, and you had your cup sitting on the counter, so would that energy flow out of the system, flow out of the cup of coffee, or would it flow into it? Where's the energy going to? So when we do Q, we want to put some subscripts. There can be Q of the system, and there can be Q of the surroundings. Q's can also be positive or negative. And like what we talked about before, if something's gaining something, if it's gaining energy or gaining whatever, by definition, that change would be positive. So if our system, if our chemical reaction is gaining energy, then that Q of that system would be positive. So that's what this is saying. The Q of the system would be positive. If a chemical reaction, if we lose chemical energy to the surroundings, then that Q of that system would be negative. If the heat flow is out of the system and going to the surroundings, that's Q system is negative, then that's an exothermic process. If the Q is positive, energy is flowing into the system, then that's an endothermic process. When you have this transfer of energy into or out of the system, it needs to come from somewhere. If the system is gaining energy, it's gaining that amount of energy from the surroundings. Meaning if the Q of the system is gaining energy, the Q of the surrounding is losing energy. We don't lose or gain, or we don't destroy energy, so whatever the system gains, it's the same energy number from the surroundings. One's positive, one's negative. So we can come up with this relationship. Q of the system equals the negative, the Q of the surroundings. One's positive, one's negative. They're exactly the same number. And that's what these diagrams below are trying to illustrate. If energy is flowing into the system, well, it's coming from the surroundings. In that case, that's an example of endothermic. For exothermic, whatever heat energy that the system loses, it goes into the surroundings. If something's losing it, that Q is negative. If something's gaining it, it's positive. Where the energy is flowing to the surroundings, that's an exothermic type of process. Note, just be a little bit careful when you look at some of the terminology in the textbook. They give Q values, aren't always the best about putting system or surroundings when they give you a problem. These equations are in your information packet, and I think I've been pretty good about giving the correct subscript for some of the different relationships. And note that the sign of Q, it's important to get that correct. Not just the number, not just the heat, but the sign, whether it's negative or positive, tells you which way the energy is flowing. You have to be extra careful when we're working on these problems and understand what negative and positive means. Having a negative heat doesn't mean it's negative energy. The negative just tells you which way the energy is flowing into or out of the system. So on this page, we're going to add another letter to your alphabet. We've introduced Q, we've introduced U, heat and internal energy. On this page, we're going to bring H to your vocabulary. H is an abbreviation for another energy term called enthalpy. What exactly is enthalpy? It's an energy, and it's an energy state of our chemicals. U and its energy is part of enthalpy. So what was U again? U is the kinetic energy and potential energy of a reactant or a product. H is internal energy plus the pressure and volume at a particular condition. And you don't quite know this yet, but pressure and volume, those units are actually energy units. And we'll see how that makes sense in just a second. So let's revisit internal energy, and in particular internal energy change. So the change of U equals the change of kinetic energy plus the change of potential energy. And again, the change of kinetic energy, well, that depends upon a temperature change. The change of potential energy, well, that includes any attractions that are part of our system. In our system, our attractions are chemical bonds and the attractions between chemicals. That sort of explains why this part of the H equation, well, that's an energy term. So what about P and V, pressure times volume? How would that be related to energy? How would that give you energy units? And a good way to visualize it experimentally, say you had this experiment and you added sodium to water. And when this reaction happens, a gas is produced. And that gas creates a change of volume. And that moves the piston upward as the gas is being produced. And maybe it's moving some mass upwards. You're moving mass upwards against gravity. That's work, that's energy. So the change of volume and whatever that pressure may be, that volume and that pressure, that eventually leads you to energy units. And you also see this when we've looked at our R constants. You see those different values of R as you change units. Some of them had atmosphere and liters. That's the traditional R that we had. Well, some of them have energy units, and we could go through those changes and see how we get joules out of it, but the R could be expressed in terms of joules per mole. We'll see that later, spring quarter, but the pressure and volume, that's related to how much work can be done. That volume expansion can do work. So H, what does it have? Well, it has kinetic energy, it has potential energy, and it has work that's part of its expression. Spring quarter, we're going to revisit H in more detail, and we'll look at work. This quarter, we're not going to look at it, but the work equals the pressure times the change of volume. And we'll be using this equation spring quarter. For this quarter, we're not going to worry about it, and I'll explain why as we go through some more derivations. So, enthalpy is an energy term, and it encompasses internal energy as part of it. So it's kinetic energy, potential energy, and pressure and volume. when chemists look at energy change, just like we did for you, we care more about the change in enthalpy. Change is always final minus initial, so the enthalpy of the product minus the enthalpy of the reactants. And writing that with a few more terms, the change of enthalpy, the change of kinetic energy plus the change of potential energy plus the pressure times the change in volume. So wasn't there a change next to pressure? Well, that's assuming that we're running our reaction open to the atmosphere, so there's no change in pressure. So, what else are we going to do this quarter? Well, we're going to run our reactions so temperature is constant, so the change of kinetic energy is constant. We're also going to do reactions in which the volume is relatively constant, meaning there's no gases produced. So what happens to our change of H? If we run our experiments this way, where there's no change in potential energy, there's no change in volume, and pressure is constant, then the total energy change, that delta H, well, that equals the change of potential energy for our system, which is the change of chemical energy. So running reactions this way, that change of energy that we see or feel, since we can't really see heat, that's the change of energy, chemical energy, between the reactants and products. So how are we going to measure this and get a delta H for a reaction, an enthalpy change for a reaction? Well, we're going to design it so we have our system, and surrounding the system is going to be water molecules, meaning we're going to have aqueous-based reactions. And all we're going to do is measure the temperature change. And that's going to tell us the energy flow. It's going to tell us the heat. So how would we get that? So how would a temperature change get that? How are we going to get the heat flow? Well, Q is based upon the temperature change. So let's write down the equation for Q. When we do this experimentally, if we have surrounding water molecules, if we know the mass of that water, and we know the specific heat of water, that's given in our information packet, and experimentally, if we measure the initial temperature of that water and then the final temperature of the water, that'll tell us the heat flow that's coming from the chemical reaction. So we're having water to collect the energy that's coming from our exothermic reaction that we're going to do on the last day of the quarter. That is our Q value, and that also means that's our delta H value. That's our enthalpy change. That's our energy change for this chemical reaction. This is how a lot of the reactions are determined experimentally, and we're going to see a listing of delta H's for various chemical reactions. By the way, spring quarter, we're going to introduce one other energy term that's part of a chemical reaction. We're going to get into more detail, but there's something called entropy that happens during a chemical reaction, and it's also energy based. That's going to give some more information about why chemical reactions happen. But for right now, we're just going to focus on delta H, the enthalpy change for a chemical reaction. And for this quarter, we'll assume that's the only energy change. Enthalpy changes for the vast majority of reactions that we know about have been determined experimentally. And shown on this page are examples of enthalpy changes for a few different reactions. This delta H can be negative or positive. If it's negative, it means it's releasing energy and it's exothermic. So our delta H value here, the negative 91.8 kilojoules, that's exothermic. If it was positive, it would be endothermic. So this delta H of negative 91.8 kilojoules, so what exactly does that mean? I mean, is that 91.8 kilojoules if a certain amount reacts? What does that mean? Well, the 91.8 kilojoules, it's in reference to how many reactants are reacting, how many products are being formed, and it goes along with the mole-to-mole relationship. So if we were going to write a mole-to-mole relationship for this chemical reaction, it's a 1 to 3 to 2 mole relationship that exists between those chemicals. That 91.8 kilojoules, well, that gets tagged along with that relationship. So this says if 1 mole of nitrogen, N2, reacted, well then 91.8 kilojoules of energy would be released. Also says, well, if 3 moles of hydrogen reacts, then 91.8 kilojoules worth of energy would be released. This delta H gives you a relationship of energy to moles. Note, and I'm sure some of you are asking this, you notice I didn't put the negative there? That's optional. The negative is just telling you that it's an exothermic process. If you just want to write 91.8 kilojoules with this relationship, I'm fine with that. You can always include the negative if you want. Don't have to if you don't want to. So if we were going to make mole to energy relationships, you could say 91.8 kilojoules per 1 mole of nitrogen. And again, you could put the negative there if you wanted to. Or you could say 91.8 kilojoules for every 3 moles of H2 that reacts. And you can include the negative if you want to. But the enthalpy gives you a mole to kilojoule relationship, a mole to energy relationship. Mole to mole, mole to energy. You can use this relationship in our favorite stoichiometry problems, which we're going to do on the next page. Also note that the delta H, the way it's presented here, it's given as just kilojoules. Sometimes it's given kilojoules per mole. And that's the way it's presented in your information packet in tables of delta H's. And that's probably the best way to present it. But you need to realize that it's per mole. And then you also have to realize, which makes it a little harder, it could be per 1 mole, or it could be per 3 moles, or it could be per 2 moles. It just depends which reactant and which product you're talking about, and what are their coefficients in the balanced chemical reaction. Shown down on the bottom of the page is another delta H for a chemical reaction that we've done in the laboratory. Hydrogen plus oxygen forming water. That was an exothermic reaction, lots of energy released. That energy that caused the sound waves made a few of you scream. And I like it so much that I showed it twice, except that's a different delta H. That's strange. Oh, what's different? If you look at it, the product in both cases is water, but one of them it's a gas and the other one it's a liquid. The net energy change, the delta H, well, for some reason it's bigger if it goes all the way to a liquid. Why would that be? Well, let's look at it. So H, what's the enthalpy of the reactants? So our reactants are hydrogen and oxygen. And they start at some H value. And again, it's relative, but somewhere up here is the enthalpy of our hydrogen and oxygen. If that hydrogen and oxygen in their gas phase reacted and formed gaseous water, that's an exothermic process, and the change of energy, it's negative, is 483.7 kilojoules for every 1 mole of oxygen that reacts, or for every 2 moles of hydrogen that reacts, or for every 2 moles of water that's produced, gaseous water. So putting that into our diagram, water is, its enthalpy is negative 483.7 kilojoules. It's that much less. The liquid, well, if water goes to a liquid, from a gas to a liquid, so maybe we should write G right there because it's in gas. The liquid is at a lower enthalpy state. And you can think about that. If you had gaseous water and it condensed into a liquid, energy's released. Vice versa, if you wanted a liquid liquid water to become a gas, you have to add energy. So H2O, the liquid, is at a lower energy state. And from gaseous water to liquid water, that's an additional 88 kilojoules worth of energy for every 2 moles of water. So negative 88 kilojoules. Or if we look at the first one, to go from H2O O2 all the way down to liquid H2O, that's a negative 571.7 kilojoules. It's really important to know what phase your reactants and products are in. It makes a big difference for the net change of enthalpy. Molecules being next to each other in the attractions, that potential energy adds to the total internal energy, which adds to the enthalpy. So when we look at this, you have to include phase when you look at the enthalpy changes. And when we start using thermodynamic tables, be careful when you look at phase. Okay, another thing about enthalpy change, this reaction showing hydrogen plus oxygen forming water, we can do the reverse. We can take water and form hydrogen and oxygen. You can take liquid water and some energy and form hydrogen and oxygen. We do this all the time. You can commercially buy a solar cell that takes the sun's photons and that energy and some liquid water, you can form hydrogen and oxygen. It's called electrolysis. Or you could take thermal energy, the kinetic energy. They do this in some countries. The thermal energy plus some water, they're moving really fast. That kinetic energy can be used to provide chemical energy to form hydrogen and oxygen. The point is, if you go from hydrogen and oxygen to liquid water, you lose 571.7 kilojoules of energy. If you want to go the reverse direction, it's the same number, but it's positive. So what if we wrote the chemical reaction as water forming hydrogen and oxygen? The delta H is the same number, so we're going from liquid water to hydrogen plus oxygen. So that delta H is 571.7 kilojoules, but instead of being negative, it's a positive number. And the point being, and we'll see this later on when we do some problems, if you reverse a reaction, make the products reactants and the reactants products, that delta H is the same number, but you need to change the sign. So shown on this page are a couple embedded practice problems, and these are stoichiometry problems. So we have our chemical reaction, we could come up with a mole-to-mole relationship, but what's new is the fact that we have an energy term that can be combined with this relationship. So before we even start the problem, write the mole-to-mole relationship for all the reactants and products, and then tag along that delta H number and include an energy term in your relationship. So pause the video, do that, and then unpause the video. There's our mole-to-mole relationship. In this stoichiometry problem, there's an A. So go ahead and figure out your A, and then think about the B. So pause the video, mark your A, and mark your B. So being told that you have 454 grams of glucose reacting, that's our A. As far as our B, well, it's not a reactant or a product, it's the energy term. Calculate how much energy is produced. The energy is actually our B. If we looked at our information packet and our outline of stoichiometry, we're actually starting with our grams of A going to moles of A. We don't have to go to moles of B. We already have our A and we have a mole to energy relationship. We can go directly from our moles of A to energy. Meaning when we do our flow of units, we can go from grams of glucose to moles of glucose. And then using our mole to kilojoule relationship, we can go to kilojoules. Note though that the problem wants us to go all the way to kilocalories. So we'll need to take that one step further, and using our information packet, we can get a relationship between kilojoules and kilocalories. But the important part here that we're learning is the chemical reaction gives you a relationship between the moles of A and the energy when you have the delta H for a particular reaction. The goal for this type, though, you have to get to moles of A always, and we're using the mole to kilojoules relationship. So if we start with grams, we need to get it to moles. Or if we started with any quantity of our A, we still need to get to our moles of A. So pause the video and get all the way to kilocalories. Using the molar mass of glucose, we know we have more than 1 mole of glucose reacting. The relationship of the chemical reaction says for every 1 mole of glucose, there's 2,870 kilojoules of energy that's released. And note, you don't have to include the negative sign when you do that. That's optional for my problems that I'm going to grade. So more than 1 mole is reacting, so it makes sense that the amount of energy that's being released is greater than 2,870 kilojoules. And as far as kilojoules, it's 7,232.5 kilojoules of energy would be released if 1 pound, 454 grams of glucose is metabolized via this reaction. As far as getting it all the way to kilocalories, for every 1 kilocalorie, it's 4.184 kilojoules. And our final answer is negative 1,728.6 kilocalories. So just to get you a frame of reference, remember kilocalories is the same thing as the nutritionless calories, what's on our food label. Meaning if you metabolize 1 pound of glucose, 1 pound of carbohydrates, that would provide your body, give you approximately 1,700 calories worth of energy. And just remember, you metabolize, just sitting around and studying chemistry all day, about 2,500 calories per day, 2,500 kilocalories per day. So let's look at a reaction, similar reaction for a triglyceride, which are fat and oil molecules. And shown below is the net reaction of a type of triglyceride that could be metabolized in your body. And this is for every 2 moles of that triglyceride, this is how much energy would be released. It's an exothermic process. It's also for 1 pound, slightly different stoichiometry relationships, but how much energy could you acquire if you metabolize 1 pound of fat or oil molecules via this reaction? So go ahead and pause the video. Very similar, different reaction, same mass quantity. Pause it and see what number you get. Unpause when you're ready to check your answer. The molar mass of our triglyceride, well, it's the same triglyceride we've used as example problems before, but it's, the molar mass is about 723 grams. As far as using the chemical reaction for our recipe for our relationship, the chemical reaction says for every 2 mole of the triglyceride, around 55,000 kilojoules worth of energy is released. So we get the other relationship, a mole to energy relationship. And again, whether you put the negative there or not in front of the 55,640 kilojoules, it's okay. But that gives you a mole to energy relationship. The answer in kilojoules, if 1 pound of the triglyceride is metabolized, is around 17,000 kilojoules. And going all the way to kilocalories, it's almost 4,200 kilocalories worth of energy would be released. 4,174 kilocalories, or 4,174 nutritionless calories. So what does this mean exactly? Just for a little bit of comparison's sake between carbohydrates and fats. The energy density, so how much energy you could harness per gram amount of these fuel molecules, there's a lot more in the fat molecule. How much energy per pound, it's greater for the triglyceride. Another thing, if you wanted to actually burn off some fat molecules, how much energy would you have to do? How much work would you have to do to use that amount of fuel? You'd have to do, on top of your normal normal metabolism and your daily intake of fuel calories, around 4,000 kilocalories worth of energy. So if you wanted to burn 10 pounds of fat, you'd have to do about 40,000 kilocalories worth of work. So those info commercials that you shouldn't be watching, that you can't sleep so you watch a little bit, that say you lose 10 pounds in a few days or a week, hopefully it doesn't make sense after doing some of these calculations. Maybe you did lose 10 pounds, but if that did happen, it's probably related to, yeah, you got it, water weight. Experimentally, how do chemists measure the energy change for a chemical reaction? So the heat of a reaction. The device that we use is called a calorimeter. It's the common device that's used. And this device collects the energy that comes from the system, from the chemical reaction, from the reactants and products, or it measures how much energy flows into the system from the surroundings. If this box represents our experiment, and within that experiment you have your chemical reaction, you have your system. Around that system, surrounding that system, you want to have material that collects all the energy that may flow from the system, or all the energy that goes into the system comes from that surrounding material. In our simple experiment that we're going to be doing in the laboratory, the surrounding chemicals are water molecules. In our simple setup, our simple experiment, if that was a exothermic reaction, so energy flowed from the system to the surrounding, we'll assume that all of the energy that comes from the system that flows out will be taken up by the water molecules. So there's going to be some heat. If energy is flowing out, we'll assume that all that energy that flows out of the system becomes kinetic energy of the water molecules. So if it's an exothermic reaction that we're studying, then those water molecules would move faster, meaning the temperature would increase. For this type of exothermic reaction, the potential energy of our system, of the reactants and products, that potential energy eventually becomes kinetic energy of the surroundings. If the reaction was endothermic, so the products are gaining potential energy compared to the reactants, you got to get the energy from somewhere, and in that sort of reaction, where is it coming from? Well, it's coming from the kinetic energy of the surrounding water molecules for the experimental setup we're going to design. So we'll write that down. In our experimental setup that we're going to do in the laboratory, that box that defines where our reaction's happening in, it will be made of a material that doesn't conduct heat very well. So the energy that goes into or out of the system is coming from the water that surrounds the reactants and products. This setup is also going to be open to the atmosphere, so there's no pressure change, and we're also going to do a reaction in which there's no change of volume of the system molecules, i.e. no gas produced or used up. We're not going to have any work that's going to be done. So when we do this, we're designing a setup so that the change of chemical energy is the only thing that's happening to the system molecules. No work change, no kinetic energy change. The chemical reaction we're going to do in the laboratory is a neutralization reaction, hydrochloric acid and sodium hydroxide. It's AQ, meaning water's the medium in which the reaction is occurring. Like we mentioned earlier, for any aqueous solution, if water's a solvent, that water is the surrounding. It's part of the surroundings. Even if it's part of the reaction, the vast majority of the water molecules in your reaction flask will be just the surrounding molecules. It's a pretty good assumption for the experiments we're doing. So here's our chemical reaction. We're going to do it in an insulating flask, and something that's pretty good is a styrofoam cup. And that's what's shown here. It's a really good insulator. Of course, there's heat transfer. Your cup of coffee gets cold in a styrofoam cup over time, but the rate of losing heat to the surrounding air molecules through the styrofoam cup is very, very low compared to how quickly the reaction happens. So we'll assume as the reaction happens and there's a temperature change for this reaction, during the time that we measure a temperature change of the surrounding molecules, virtually all of the energy that is given off or taken in is going to the water molecules or from the water molecules. Also, it's open to the atmosphere, so instead of going through the polystyrene, it could go just collide with the air, but that rate is also pretty slow. So our main assumption experimentally is that the energy exchange between the system and the surrounding for that minute or two that we're going to analyze it is just the water molecules. So how do we measure how much energy the water collects or gives off to the system? We don't have a device that can measure joules. You can't just put something into water and measure the joules. But we do have our equation with Q. So Q is the heat that flows into or out of a system. That's the energy change that's going into and out of a system. If you wanted to measure how much is going in or out of the water, well, you need to know a few things. You need to know how much mass of water is in your container that's surrounding your system. And since we're looking at water, the flow of energy into or out of the water, we're going to use the specific heat of water, which is in your information packet. And we need to know the temperature change. So what's the initial temperature of that water, and what's the final temperature of the water once the reaction is complete? Final minus initial. So this is measuring the energy change that goes into or out of the water. It could be negative, it could be positive. It depends upon what's happening to the change. So when you do this experimentally, before the reaction starts, you need to figure out what's the initial temperature of that surrounding water molecule. You need to measure what's the mass of that water, and then you'll mix the chemicals together and see what the highest temperature is. That's your temperature final. This gives us the heat that flows into or out of the surrounding water molecules. So this is Q, but more specifically, it's Q of the surroundings. So we'll put a circle around that. That just tells us the heat flow. And that's not really a relative number. For example, if you burned a gallon of gasoline versus 10 gallons of gasoline, the heat that flows from it's going to be different. But if you wanted to know what's the relative amount, how much energy per gallon, you need to get something that's relative, and that's what delta H gives us. Q is the total energy, the heat that flows, but delta H is how much heat flows per amount that's reacting, or per amount that's being formed. And our delta H is Q of the system divided by how many moles are reacting or moles that are being formed. So delta H is called the enthalpy change. It's also called the heat of the reaction. And again, most of the time it's expressed how much energy per mole. And you have to be a little bit careful, like we explained earlier. It's mole per whatever number that it is in front of the molecule in the balanced chemical reaction. The reaction we're looking at experimentally, it's all a 1-to-1-to-1 mole-to-mole relationship. But nonetheless, experimentally, when we do this eventually to get the heat of a reaction, the enthalpy change, we're going to experimentally determine the heat flow into the surroundings. And we also have to experimentally figure out how much is actually reacting. And also remember that the one last relationship, Q of the system equals Q of the surrounding, and negative. One's positive, one's negative. We assume all the energy that flows from the system goes to the surrounding, or vice versa. It's the same number, but one's positive, one's negative. So let's take this information from this page and do some practice problems that are very similar to the laboratory that we're going to be doing, and probably very similar to a really hard problem that'll be on your exam. On this page is an example problem to calculate the enthalpy change, the heat of a reaction for a particular reaction. Go ahead and pause the video, read through it, and either try and solve it all on your own, or unpause and see how the problem's getting set up. The end part of this problem is you're trying to figure out the enthalpy change for this reaction, this acid-base reaction. So when we do this, there's two measurements you have to make or calculate. Since we're doing a paper problem, you need to know how much energy is flowing from the system to the surroundings, or vice versa, and how much of the chemical is actually reacting. Remember, the enthalpy change is the energy change per mole. We need to find the heat flow, the Q of the system, and the amount that's reacting, that mole quantity. Or you could, how much quantity is being formed. Either way, but we need to get the amount of energy per mole. The heat flow, and the more reactant you have, the more heat that's going to flow, but it's a relative number. For example, if you burn 2 gallons of gasoline, there'd be a certain amount of heat that would flow in that exothermic process. If you burned 3 gallons of gasoline, there would be more heat flow, but the heat per gallon would be the same for either reaction. And that's what the change of H, the change of enthalpy, gives us when we have it energy per mole. So we need to know how many moles are reacting or produced. We'll find a chemical there. And we need to know Q, is that heat flowing from the system or into the system? As you read through the problem, you see that KOH is in excess, meaning this reaction is limited by how much HBr is reacting. You're told the volume of that aqueous HBr solution, how much is reacting. We can use that information to figure out how many moles of HBr reacted. And that'll be our bottom part, our bottom measurement for delta H. So that volume and that molarity concentration will allow us to calculate how many moles of HBr are used. As far as Q of the system, so what's going on, how can we tell how much energy is flowing from the system to the surroundings? So in our diagram, we have water. This is an aqueous solution, meaning water is the surrounding. And we assume that all the energy that either flows into the system or out of the system, it goes either into the water molecules or from the water molecules into the system. So we have solvated ions moving around, HBr and our KOH, those respective ions floating around. When that reaction happens, the surrounding molecules are the water molecules. And again, even though water's a product, the vast majority of the water molecules in there are surrounding water molecules. And we'll just assume for our test that they all are. The calorimeter, it's an insulator, so we assume that none of the energy change goes into the walls of the calorimeter and eventually to the air molecules. That transfer does occur eventually, but it's pretty low for how quickly this reaction, this test would take place. If we look in the problem, we also see that the temperature increases. The temperature. We're measuring the temperature of the surroundings. We're measuring the temperature of the water. The temperature is going up, which means the velocity is going up, which means the kinetic energy is going up. This is an exothermic type of reaction, and your delta H, when you calculate it, should be negative if it's exothermic. So what does this mean? What's going on when this reaction happens? The chemical energy, the potential energy in the system, the reactants, well, those reactants lose some of their potential energy, and that heat, that energy that flows away, becomes kinetic energy of the water molecules. And the water molecules move faster, which means the average velocity is faster for the water, and the temperature is a reflection of the average speed, so the temperature increases. So hopefully when we're done, your answer should always make sense. Hopefully that enthalpy change is a negative number. And enthalpy is with respect to the system. It means the system is losing energy. Whenever something loses anything, whether it's energy or whatever, that change is always negative. If it gains something, that change would be positive. Our system, our reactants, are losing energy, so the delta H should be negative. So, how much heat was collected by the water molecules? What's the Q of the surroundings? Well, the temperature change is part of that equation, and the heat flow that went into the surrounding water molecules, well, it depends upon the mass of the water. It depends upon the mass of the surroundings, and in this case it's water. So it depends upon the mass of the water. Water's surroundings, we're going to use its specific heat constant, which is 4.184, and we'll use that temperature change. The heat is flowing into the water, so hopefully we get a Q value for the surroundings that's positive. The final initial temperatures are given in the problem, so we'll just plug those into there. But what about the mass of H2O? How much surrounding water? What's the mass of that? Well, what do we know from the problem? We know the volume of solution that was added from each one. And if we add those two up, we get 50 milliliters of solution once all the KOH solution and the HBr solution is added. So the total volume, which includes the water and all of the solutes, we're going to make a little bit of an assumption here. It's not a perfect assumption, but it gets us really close to the answer. It's 99.9% correct. But that total volume, we'll assume that that's the mass of water. If the density of the solution is 1 gram, then if there's 50 milliliters of solution, then we have 50 grams of solution, and we'll assume that that total mass is 50 grams of water. So this volume becomes grams using the density of the solution, and we'll assume that the mass of the solution is the grams of water, and we'll plug that into our equation. So 50 milliliters of solution eventually becomes 50 grams of solution, and we'll plug that into our heat expression. So knowing the grams of surrounding water, the specific heat for water, and the temperature change, we can calculate Q. And when you plug in the numbers, you get a positive value for Q, 1255.2 joules. That should make sense. The surrounding water molecules, that's the direction the energy is flowing. So the Q value for the surroundings, the water, is positive. And we also assume all of the heat that flowed into the surroundings was coming from the reaction, or all the energy lost from the reaction from the system flowed into the water molecules during that initial time of the experiment. Eventually that energy will flow off to the surrounding air molecules, but it's pretty slow through a styrofoam cup. So that's our Q of our surroundings. Since Q of the system equals the negative the Q of the surroundings, the Q of the system, which we need, the value of the number is the same except it's negative. The system, our chemical reaction, is losing that much energy. Now, as far as calculating the bottom part, since we have, this number will go into that part of delta H, we still need to calculate how many moles of HBr actually reacted. We know from the problem that HBr was the limiting reagent and 20.9 milliliters reacted. The concentration was 1.07 moles of HBr per liter. So using the volume that reacted and its concentration, that'll tell us how many moles of HBr actually reacted, was used up. And there we go, 0.02236 moles of HBr reacted. We can take that number and plug it into the equation and take the energy flow, the Q of the system, and plug it into the equation and get our enthalpy change. And the enthalpy change is 56,128 joules per mole, and it's negative. So that's an exothermic process. The delta H is negative. And that's what we predicted in the beginning by looking at the temperature change of the surrounding water molecules. A note, it doesn't matter how much reactant you reacted. If we would have used more HBr, our Q of the surroundings would have been a bigger number. But that ratio of joules per mole, that 56,128 number, that should be the same no matter how we set up our experiment. In the last few slides, we talked about a calorimeter in which the only surrounding material was water molecules. On this slide, we're going to look at the heat of reaction using a different type of calorimeter. And instead of just having water, there's other material that's going to absorb the heat from the reaction, or the energy is going to be taken from that material. This type of device is called a bomb calorimeter. In the previous examples, it was just water that was absorbing the heat or releasing the heat to the system. So we needed to know the mass of just that water. In this one, there's water surrounding the reaction chamber, but there's also metal and other components that could absorb or release heat to the system. So shown down here is an example of the device. In the very center of the device would be the reaction chamber, and it's surrounded by some sort of conducting material. It could be some sort of inert metal relative to that reaction, and then surrounding that chamber all around it is water. So when heat flows in or out of the system, the surrounding is the water plus whatever material is making up the reaction chamber. The very exterior would be insulating, and there would be some sort of thermometer that measures the temperature change of the water. So in this device, you can't just say it's water, so we can't use the specific heat of just water. What you do is you calibrate this device, and you get a constant for this device that's specific for this one. Some of you that go on to physical chemistry will use this device in your experiment, and you'll have to calibrate your device instead of just measuring the mass of water in your calorimeter. That constant for the device is called heat capacity. So instead of specific heat that's specific for one particular material, we have a heat capacity constant for that device. And if you remember from our previous slide, we had equations for heat, for Q, if we knew the specific heat of a particular material, and that's the equation we've been using in the last slides. The one we're going to be using that has heat capacity C, which is a constant for a device, the change of temperature times that constant for that device. So this device would have a heat capacity. And the units for heat capacity would be joules per degrees Celsius. The surrounding material would be a combination of different things, but water would be part of it. The metal that's part of the reaction vessel that's surrounded by the water, that thermometer that's in there, all the material that's in that device that's surrounding the system and within the insulating walls of the exterior of the device. And the heat flow, the Q of the surroundings, would be the heat capacity C times the temperature change. And again, each bomb calorimeter would have its own constant, and you would probably have to calibrate it every time you used it. If you're going to have a problem like this on your exam or practice problems, this constant, this heat capacity, would be given within the problem. It's nothing you'd find in the information packet. Each device is a little different, and on the next page we're going to see a problem where we're going to calculate the heat flow to the surroundings, and it's a reaction that's happening within a bomb calorimeter. Also note in this device, in this bomb calorimeter, you can actually add heat. Some reactions take an initial amount of energy to get them going, And within the reaction chamber, there's some sort of ignition coil. And in fact, when you calibrate the instrument, you know how much energy these coils are putting out, and it's used to calibrate and determine the heat capacity constant for this instrument. But for now, let's practice a problem, a paper problem, using heat capacities to get the heat flow into the surroundings. Here we have an embedded practice problem. Go ahead and pause the video, read the problem, unpause the video, and let's make sure we're going down the same path. So when we read the problem, what are we solving for? We're trying to get the enthalpy change. So the delta H, how much energy per mole? You're doing this reaction in a calorimeter, and you know it's a bomb calorimeter type of device because you're given heat capacity. The surrounding it's more than just water. But with that constant and the temperature change, you can calculate the heat flow into the surroundings. Temperature increased, so you should be able to tell from that whether your Q of the surroundings is positive or negative. Once you have that, that'll tell you the joules of energy, the joules of heat. Then, the other part, so we can get that part to get moles, how much is actually reacting. We have the gram quantity, and I think you know what to do to get it into mole quantity. So pause the video and go ahead and unpause when you're ready to check your answer. So the heat capacity says for every 1 degree rise in temperature, there's 1258 joules worth of energy. That's the amount of energy that must be flowing into the surroundings. So since we have a larger temperature change than 1 degree Celsius, we're going to have more than 1258 joules. And our calculation is 17,234.6 joules. That's our Q of our surrounding. It's positive because heat is flowing into the surroundings. The Q of the system is the same number but negative. It lost that amount of energy. So negative 17,234.6 joules. And we'll take that number and plug it into our enthalpy change. So we have part of that proportion. Now we need to calculate N to find out the actual amount of moles that reacted. 23.6 grams of calcium chloride. Let's get its molar mass and convert that into moles of calcium chloride. And the mole quantity is 0.212 moles of calcium chloride. That's how much reacted. So we'll put a circle around that, and we'll take that mole quantity and plug it into our enthalpy calculation and solve for that number to get joules per mole. So this is an exothermic process. The chemical energy in the reactants became the kinetic energy of the surrounding water molecules and the surrounding metal that is part of that calorimeter device. The water's moving faster, and the solid material, the metals or atoms, are vibrating with more velocity, higher kinetic energy, i.e., a higher temperature. The next concept we're going to talk is Hess's law, and this concept's been around for a long time. And this law is looking at energy changes, and we're going to apply it to a few different applications. But a nice way to think about it, what if you had a beaker and there were different reactions that were happening in that beaker? Some reactions maybe released energy, maybe there's some other reactions in there that took in energy. What's the net energy change that would happen in there? Or let's even think some sort of physical example. Say you're in a building, and it's a really tall building with lots of floors. So this is my very artistic drawing of a building, and there's 7 floors in there. Say you were on the 3rd floor. So that little stick figure, that's you. and you went up and down between floors. What's happening to your potential energy? So maybe you went up to the 5th floor, and then you went all the way down to the 2nd floor. And then maybe you went all the way up to the 7th floor, and then you went all the way down to the 5th floor. And that's where you stayed. There was a lot of potential energy change there, but what's the net change? Your net change is from the 3rd to the 5th floor. Hess's law applied to chemical reactions, what exactly does that mean? Well, what if you had a beaker and you had a series of reactions going on? So you had a variety of different reactions going on in your beaker. Some were exothermic, some were endothermic. Some released energy, some took in energy from the surrounding. What's the net change after that series of reactions? That's what you'd use Hess's law for. And on the next page, when we get to it, we'll show an example of that. But let's say it in terms of chemistry talk, chemistry language, because we're all going to be chemists. The enthalpy, so that's a measure of the energy of either your reactants or products, where it's at. But if you go from the reactants to products, it doesn't really matter how you get there, what path you take. It's kind of like saying if you went from Spokane to Seattle, that net change, that net elevation change, it doesn't matter how you get there. There's lots of roads that lead from Spokane to Seattle. It's the same net change. Same thing for chemical reactions. If you have reactants that eventually form these products, it doesn't matter how you get from reactants to products, there's a net change. Our example in our building, you start on the 3rd floor, you end on the 5th floor. Doesn't matter how you change. Instead of going up to the 5th floor from the 3rd floor in the very beginning, we could have went down to the 1st. But if our final is the 5th and our beginning is the 3rd, it doesn't matter what path we take. Same thing for chemical reactions. It doesn't matter how the reactants form products. That net change is the same no matter how you achieve it. Shown on this page is a series of 10 reactions. And those of you taking cellular biology right now, which I know there's a number of you who are, you should recognize this. This series of reactions happens in every cell in every organism, and this series of reaction has a name. It's called glycolysis. And when glucose enters a cell, and you don't need to know this, you'll eventually learn this in biochemistry, but I'm going to explain these reactions. When it first enters a cell in your body or any organism, the first thing that happens is a phosphate gets attached and you form glucose 6-phosphate. Okay, so that's a reaction. Why we call it a series is because a product of reaction number 1 is a reactant in reaction number 2. So that glucose 6-phosphate then reacts in reaction number 2. It was a product in 1, it's a reactant in 2. And it forms something called fructose 6-phosphate. That product then is a reactant in reaction number 3. And it eventually forms this fructose 1,6-diphosphate, which is a product, which is a reactant in reaction number 4. This is what chemists call a series of reactions. They're all linked together. A product in one is a reactant in another. Eventually those carbon atoms from glucose, as you keep going through, eventually form pyruvate molecules. And relating this to Hess's law, if you look at these reactions and the enthalpy change for each individual one, some of them are exothermic, some of them are endothermic. Reaction number 1, that negative delta H, that's exothermic. So when that reaction happens, it heats up your cellular fluids. Versus something like reaction number 5, that's positive, that takes kinetic energy from the surrounding water molecules in your cell, and it becomes potential energy of the products. That's endothermic. So reaction 1 would heat up your cell, reaction number 5 would cool down your cell. But as far as the net, some of them are heating up your cell, some of them are cooling them off. If you add all 10 of these enthalpy changes for each reaction, that would be the net for the overall process. Go ahead and pause the video. Just add up all those numbers in that column, those 10 numbers, and see what you get. What's the delta H net that you get? So pause the video, unpause when you're done using your calculator. If you used your calculator correctly, you should have got a negative 18.3, and the units would be kilocalories per mole. Meaning, after those 10 reactions, there's a net amount of energy that's released to your cellular fluids. Notice another thing here. We've done net reactions a little bit. Shown on the bottom is the net reaction for the series of this 10 reactions. And there's glucose and there's pyruvate. That's weird. I don't see a lot of the molecules that are up there. So where's that glucose 6-phosphate in the net reaction? Well, when you get the net reaction, if something's produced then used up, it's crossed out. So glucose 6-phosphate is produced, but it's used up in reaction number 2. So in the net reaction, you don't see that. And you would do that for all of them. The fructose 6-phosphate is produced in reaction number 2, but it's used up in reaction number 3. So you don't see that in the net reaction. So the slide where we were just on shows us a use of Hess's law. The net enthalpy change can be calculated for a series of reactions. The other application we're going to see on the next few slides is how Hess's law is used to calculate delta H for reactions that you cannot do experimentally. There's just some experiments that you cannot perform experimentally. You can't start from these reactants to form those products for different reasons. We can use the concept of Hess's law to help us determine that energy change for a reaction that cannot be done experimentally. So let's skip ahead a couple slides. Well, not skip. Let's go a couple slides forward and see some examples of that. Here's a reaction that is experimentally difficult to do. It's taking graphite and doing a combustion reaction with oxygen to form carbon monoxide. And when I say experimentally difficult, it's difficult to mix those two reactants together and just form carbon monoxide. It's pretty easy to take graphite and form oxygen and only form carbon dioxide. It's almost impossible, as far as I know it is impossible, just to form carbon monoxide. So how can we use Hess's law to figure out the enthalpy change, the heat of the reaction for this reaction? So ultimately, we want to figure that out. The idea is really, it's no different than what we just discussed with glycolysis in that series of 10 reactions. If you had a series of reactions that you knew the delta H is for, and that series of reactions, when added together, could give you the net reaction for the one you can't do experimentally, you could use those individual ones to figure out the net change. So let's state that a little clearer. The unknown reaction with the delta H that you need to determine, consider that the net reaction. If you have a series of other reactions that when added together give you that net reaction, those delta H's can be added together to give you the delta H net. Shown below, even though there's only 2 reactions, and you can't really see it quite yet, but these 2 reactions, when added together, are going to give us that net reaction of 2 graphites reacting with oxygen to form 2 carbon monoxides. So let's go through that process. So we'll call the first one reaction 1 and the bottom one reaction 2. These are 2 reactions that it's easy to experimentally determine the delta H. So these delta H's are known. And for reaction number 1, it's an exothermic reaction, and it's negative 393.5 kilojoules per mole. The second reaction, it's also, the way it's written is also exothermic. It's negative 566 kilojoules per mole. So these are the 2 reactions, and of course they're not written so that you can just add them together and get the net one. You have to modify them a little bit. So what does that mean to modify them? If you notice in reaction number 1, in that reaction there's 1 graphite. Well, in the net reaction there's 2. What do you do? Well, the only place that graphite occurs, it only occurs in reaction number 1 and 1s. So how do you get 2? Well, you'd have to multiply it by 2. And if you multiply the graphite by 2, well, you got to double all the reactants and double all the products. The net gives you the final answer. I mean, what you're trying to do is modify your individual reactions to get the final answer. So this is the process that we're going through. So 2 graphite would react with 2 oxygens to form 2 carbon dioxides. As far as reaction number 2, I mean, sometimes you change the individual reactions to get the solution, sometimes you don't. But, I mean, you have to look at the answer to try and decide what you're going to do to the individual equations that you're adding together. And if we look at it at the net reaction, carbon monoxide is a product. In reaction number 2, it's a reactant. There's 2 on each side, but if it's a product in your final answer, it needs to be a product in your equation number 2. Meaning reaction number 2 needs to be reversed. So reaction number 2 the reactants would be the carbon dioxide. 2 carbon dioxides form 2 carbon monoxide and 1 oxygen molecule. As far as the enthalpy changes for each individual reaction for reaction number 2, if you change the reactions around, the enthalpy change, those numbers are going to change. For reaction number 1, where we times it by 2, now we have 2 graphites reacting. Before it was manipulated, it was 1. When we only had 1, the energy released was 393.5. Well, if we have 2, the energy released is double that. So if you multiply a reaction by a number, you need to multiply the enthalpy by that same number. 2 times 393.5. As far as the enthalpy change for reaction number 2, carbon monoxide forming carbon dioxide released 566 kilojoules per mole. Well, going the opposite way, climbing the reverse hill, carbon dioxide would need to take in that same amount. So if you reverse a reaction, the enthalpy change, times it by -1, so the reverse reaction would be a positive 566 kilojoules per mole. The net of those 2 reactions, just like we learned on the previous slide, just add those 2 together, and that'll give you the net energy change for the process. The graphite forming carbon dioxide would release energy, carbon dioxide forming carbon monoxide would take in energy. And the net energy change for that process is negative 221 kilojoules per mole. That delta H net of the reaction, that's the enthalpy change for that reaction. We can also check our work, and it's good to check that we rearrange these individual ones correctly. So we have these 2 reactions. It's good to see what you get when you add those 2 together. So if something's produced but the same amount is used up, you don't see it in the net process. So go ahead and pause the video, add those 2 reactions together that I circled, and that net reaction hopefully is the same as what we have up above. Unpause the video when you're ready to check your answer. So as we go through the canceling process, 2 carbon dioxides are produced there, 2 are used up there, so we don't see it in the net reaction. We see that 1 oxygen is produced there, 2 are used up, so the net is that 1 is used up. So everything that's a reactant, the 2 graphites and the 1 oxygen, will be a reactant on the net reaction. The only product we have left are the 2 carbon monoxide, so we'll write that down below. Our net reaction after we rearranged our individual ones is the reaction that we're trying to get to and find out the unknown delta H for that reaction. In this example problem, you want to figure out the delta H for a reaction in which acetic acid is formed from 5 different chemicals. This one is definitely impossible to do. Having these 5 molecules collide just right to form one molecule is definitely impossible. With that said, there's 3 reactions that could add up to give us that net reaction. Instead of making this molecule in one big swipe of the hammer, you can build it steps at a time. So let's see if that's possible. Here are 3 reactions, 1, 2, and 3, and the enthalpy change for each one is given. We need to rearrange these 3 reactions and put them in a series that shows when they're added together can give us that net reaction. So we need to do some modifying. Just note on the exam, if you have a problem like this, how you modify your individual reactions, that's going to be part of the grading. So you need to show your work on this type of problem. But again, to decide if you're going to modify any one of those 3, you need to look at your final answer and make some observations to decide, are you going to reverse it? Are you going to multiply it by a number? So pause the video and decide what you're going to do with each of those 3 reactions. Some may change, some may not. Looking at the final answer, you see that acetic acid is on the product side, reaction 1. That's the only reaction it occurs in, and it's on the reactant side. So reaction 1 needs to be reversed. And when you reverse the reaction, the enthalpy change needs to go from being negative 874 to positive 874. Just one thing to note as I wrote the delta H, it just says kilojoules, but we know as chemists that that's kilojoules per mole for that reaction. Sometimes that's not given, if you remember what I said earlier in our lectures. Okay, what about reaction number 2? Okay, number 2, there's 1 graphite, and that's the only place where graphite occurs. If we look at the net one, there's 2 graphites. So what should we do? Yeah, multiply reaction 2 by 2, and then change the enthalpy change. So if we multiply the reaction by 2, we have to multiply the enthalpy change by 2. So negative 197 times 2 is negative 394 kilojoules. So that's reaction 2. What about reaction number 3? Looking at reaction number 3, let's find a chemical in there that's also in the net reaction, and one that is hydrogen, H2. So there's H2 in the final one, there's H2 in reaction number 3. That's the only reaction that it occurs in. H2 doesn't occur in reaction 1 or 2. There's 2 hydrogens in the net reaction. There's 2 in reaction number 3. So we don't need to multiply by a number. It's a reactant in the net. It's a reactant in the product. All this means leave reaction 3 alone. It's good to go. So we'll just rewrite it, but nothing's going to change. And after doing that, we have 2 reactions that were modified, one that's staying the same. Reaction number 1 would take energy from the surroundings, and reactions 2 and 3 both would release energy to the surroundings. Adding those energy changes for each one that goes towards the series of reactions, when you add those 3 enthalpy changes, more energy is released than what's taken from the surroundings, and then net enthalpy change is negative 92 kilojoules. And that's the number that would go for our unknown reaction that's shown up above. And again, it's always good to check your work to make sure that we've modified our individual reactions correctly. So pause the video if you haven't already add these three reactions together, and that series of reactions, after they're complete, what's in that net process should agree with the reaction that we're trying to go towards. So pause the video, unpause when you're ready to check your answer. As we go through the canceling process, in reaction number 1, 2 oxygens were produced. In reaction number 2, 2 were used up. So those 2 aren't seen. When we're getting the net, there's going to be 1 that's going to be on the reactant side. Other chemicals that get canceled out, 2 carbon dioxide in reaction number 1 are used up, but 2 are produced. So in the net reaction, you don't see carbon dioxide. And the last chemical that gets canceled out, 2 waters are used up in reaction number 1, 2 are produced in reaction number 3, so we don't see water in the net reaction. So as far as chemicals that will be in the net reaction, on the reactant side will be 2 graphites, 2 hydrogens, and that 1 oxygen. What's on the product side would just be, what hasn't been canceled out is just the acetic acid. And one last note for future topics and net reactions. If you ever see a chemical reaction and there's 3 or more reactants, it's a net reaction. We'll learn next quarter that the probability of 3 or more molecules colliding just right to form that product isn't likely. And we'll learn about mechanisms and stuff, but it starts from this concept here that we've started about in series of reactions. But we'll save that excitement, that fun for next quarter. One last topic to introduce in this chapter is standard enthalpy of formation. And this is the energy change that happens when a chemical is formed from its elements, and the elements that are in their most stable state. So if you're forming water, what's its enthalpy of formation? What's the energy change to form water from elemental hydrogen and elemental oxygen? This energy change, this enthalpy of formation, is designated by that symbol, delta H, and there's a subscript F. In your information packet are a variety, quite a few enthalpies of formations for a lot of different chemicals. Shown on the next slide is an example of what you would see in your information packet. But if you had some sort of chemical like calcium, the ion, its enthalpy of formation, that energy change, is negative. If you looked at something like carbon disulfide, its enthalpy of formation is a positive number. Carbon disulfide, what's the energy change if you go from elemental carbon, elemental sulfur to form CS2? So that's kind of strange. One's positive, one's negative. This doesn't mean that it's a positive or negative energy. It's just what's the change relative to their elemental state. So this table, if we look in our information packet, starting kind of in the middle, and everything from there on are enthalpies of formation for various types of chemicals. Notice this table contains more than just the enthalpy of formation. It contains some information that we're going to be using spring quarter, which we'll save those for a little bit later. But here's our enthalpy of formation. Make sure when you do use this table, you go to the correct column. Also note that this energy change is kilojoules per mole. So let's see how we're going to use this. This enthalpy of formation, this change, is somehow going to allow us to calculate the change of enthalpy for a reaction, so the change from the reactants and products. So how does a change allow you to make a calculation of a change? Shouldn't you just have start and finish? Well, let's look at it with an analogy of being in the building again. And don't worry, I won't draw a stick figure of you again, but let's look at how a change can allow you to get a different change. So what if we had a building, there were 6 floors, and there was some object X on the first floor, and you measured what the energy change was to go from 1 to 3. So you know that energy change. In a separate experiment, you measured how much energy it took to go from 1 all the way up to 6. So you have the changes for both of those. If you have those two changes, what if I just wanted to know from that information, what's the energy change from 3 to 6? You could use those first two, these energies, and those two can allow you to calculate what it would be to go from 3 to 6. That's kind of what these enthalpies of formations are. But let's look at it a little more closely. So what are these enthalpies of formation? There's another fact that I haven't stated clearly yet. There's a 0 mark. Like for potential energy in the building, what's 0? Well, there's a definition of what's 0. And here we have a definition. If you're a pure element and you're the most stable pure element, that energy is said to be 0. The enthalpy, if you're the most stable, is said to be 0. Meaning, when we see these negative and positives, it's based upon whatever we define to be our 0 mark. And we do this in all of sciences. We need to define a 0. And we don't need to know exactly what the energy is as long as we have a definition of what 0 is. So experimentally, you can take your most stable elements and form other things and measure that energy change. And these changes, if you have it for each one, you can use that information to figure out what the change is for a chemical reaction. Another thing before we get started on some examples, these enthalpy changes of formation were done at certain standard conditions. And standard conditions, it's kind of like when we did STP for gases. There's a standard temperature, 25 degrees Celsius. If there's gases involved, it's a standard pressure. If there's a concentration, the standard concentration is 1 molarity. Why would all of these matter? Well, again, temperature is related to how fast they're moving. We're looking at H, which includes internal energy, which includes kinetic energy and potential energy. So why would we care about the concentration? Molecules are close to each other. How close they are, that there's potential energy involved because they're attracted to each other. So this delta H of formation, it depends. And they can change if you change some of these standard state conditions. This delta H of formation, it really is a change and it really does mean that. But when you look at it and you use these numbers, think of it more as that's the potential energy of those chemicals. It's proportional to that when we use it as a change for the reaction. And I know that's a little confusing, but we'll do some practicing as we go along. So it's proportional to the potential energy of that particular chemical. It's proportional to the chemical energy. And again, there's definitions, there's something defined to be 0. But again, when we have chemical reactions, we care more about what the change is. So, how are we going to use this in some problems? For the chemicals, for the reactants, what you'll do is you'll look at a chemical reaction and you can tell what all the reactants and products are. For each reactant and for each product, you'll look up their delta H of formation, and that basically gives you the relative potential energy, the relative chemical energy of each one. Once you have that, you can see what's all the potential energy of your reactants and what's all the potential energies of your products. You can add those together. That difference gives you the net energy change for a reaction. So a good analogy, so if a person's on the 3rd floor and they jump to the 2nd floor, but on the 3rd floor they have a certain amount of potential energy. If there was 4 people that jumped from the 3rd floor, then the total potential energy would be for all 4 people. You're going to use those tables, look up the potential energy of each reactant, look at the chemical reaction and see how many reactants you have, sum all those potential energies together, and you'll have sum total of potential energies for all the reactants. Then you'll analyze the products. Look at all the different products, sum up all those potential energies, and if the potential energies of the products is greater than the reactants, then it must be, is that exothermic, endothermic? Yeah, that would be an endothermic reaction. You may have the other type where all the products' potential energies are less than all the reactants, and that would be an exothermic reaction. There's an equation in your information packet that describes it, and it has some Greek in it, meaning some Greek symbols. The change is always final minus initial, so final for a chemical reaction is products minus reactants. So when you do this problem, you need to get the delta H of formation of all the products, and that N means, for each one you have to add towards the total chemical energy, potential energy of all the products. So you'll get some number for that portion, and that this symbol, that means the sum of, it means add them all together. And then you could choose any letter, but that just means sum all the potential energies of all the reactants, the delta H of formation for each reactant. That difference will give us the theoretical enthalpy change for a reaction. Now you can do it experimentally. We'll use these tables in the back of our information packet to theoretically predict what it should be. So let's go to a page and practice what we just learned. In this reaction, we have 4 ammonias reacting with 5 oxygens to produce 4 nitrogen monoxides and 6 water molecules. We're going to theoretically calculate what the enthalpy change is for this reaction. So theoretically, meaning we're going to use our tables in the back of our information packet. So for those 4 chemicals, we're going to go to the information packet and find the enthalpy of formation for each one. Let's go to our information packet, and we'll start with ammonia first. So in this table, they're grouped by the type of atom. And again, not every chemical is on here, but they're grouped by the type of atoms, and kind of they're the main atom in a molecule. So instead of going to hydrogen, we find nitrogen. Now notice there's NH3. You have to be really careful about the phase. There's NH3 that's aqueous, and the other one is gas state. The potential energies are different for it depending what state it's in, because what molecules are around it. When you're a gas molecule, there's very few molecules that are close by. Very little potential energy between molecules that add up to the enthalpy that potential energy is part of. Versus if you're solvated, there's a bunch of water molecules attracted to you and stuck to you. And we'll learn about that a little bit later. But it's really important in any of these reactions, you have to look at the phase. And so the one we're going to pick is that. And the enthalpy of formation is negative 45.9. And again, it's negative, but that's just a reference point, from what we define to be our zero. If you define, our laboratory's on the 3rd floor, that could be our 0 mark. So the 2nd floor would be a negative potential energy. But negative 45.9, it's just a relative number. We'll take that one. If we go and look for oxygen the gas, it's 0. And we could do the same thing for nitrogen monoxide. Oh good, I picked ones that are on the same page. It's 90.29. And lastly, water, and be a little careful, water gas, water liquid. In our equation, it's water the gas, so negative 241.8. So we'll put all those numbers below our chemicals in our example problem. I didn't point it out when we were in the information packet, but the units are kilojoules per mole. So if we had 1 mole of NH3, it'd be negative 45.9. But another thing to pay attention to in our chemical reaction, that negative 45.9 is for 1. Well, we have 4. So we need to, when we do our total potential energies, well, there's 4 of them, each one at negative 45.4. There's 5 oxygens, but it's, each one is 0, so we'll still put it in our formula so we kind of see, where it goes, but it's 0. Nitrogen monoxide, there's 4, each one at 90 kilojoules per mole, and water, there's 6 at negative 241.8 kilojoules per mole. By the way, that's, negative 241.8, that would be the lowest potential energy. That'd be like for you in this building, your lowest potential energy is when you're on the ground outside. Your highest would be when you're on the 3rd floor. Water, of all those chemicals, has the lowest potential energy. Okay, let's put these numbers into our equation. So we need to sum up all the potential energies of the products and sum up all the potential energies of the reactants and see what the difference is. And that's our enthalpy for the reaction. Here are those numbers putting it into that equation. So final minus initial, products minus reactants. In red are the potential energies of all the products. In blue are the potential energies of the reactants. I know oxygen was 0, and you don't have to show that if it's 0, but we're just learning it, so it's a good thing to do it at this point. And the units are kilojoules per mole. The sum of all the potential energies of the product is negative 1,089.6 kilojoules per mole. The sum of all the potential energies of the reactants is negative 183.6 kilojoules per mole. And again, note this, the fact that they're negative, it's just based upon what we say is 0. But that difference is the enthalpy change for the reaction. And note, I didn't put this little knot that goes there next to the H. That just means at standard state conditions. But that difference is negative 906 kilojoules per mole. If we kind of wanted to draw a diagram to illustrate that, where are the potential energies, relatively speaking? What are the potential energies of the reactants, and what are the potential energies of the products? And again, the units would be kilojoules per mole. And this is really the delta H of formation. But the reactants, when we start the reaction, they're at negative 183.6. The products, when they're formed, their potential energies are negative 1,089.6. So starting at negative 183, going down to negative 1,089, that's our delta H, our enthalpy change for the reaction. And this would be like if I defined the 3rd floor to be 0, going from the 2nd floor to the 1st floor, that would be our change. The 2nd and the 1st floor would be defined to be negative. Don't get hung up with the fact that the potential energies are negative. It's just based upon our definition. And chemists, we have our definitions, but what we care more about is the fact that we've measured the change. So negative 906 kilojoules per mole.
Now we're going to shift gears and talk about reaction rate. And reaction rate, this is how many chemical reactions are happening per time. Rates are always a change. And here we're going to talk about rate of a chemical reaction. Again, it's the number of chemical reaction per change in time. That triangle means change. Okay, so how do we measure that? Well, we don't have anything in our laboratory that can count reactions as they're happening. They're too tiny. But what's happening when you have a chemical reaction? Well, you start producing product, and as you produce more and more product, there's a higher concentration of the product. So another way of calculating rate, another way to express it, is the change of concentration per change in time. Chemical kinetics, that's the study of reaction rate. Rate of reaction is related to the energy to break the bonds and colliding in the correct orientation. So nothing's really changed, but anything you can do to make it easier to break bonds or collide in the correct orientation will increase reaction rate. If you make it harder to break bonds, if you make it harder to collide in the correct orientation, then reaction rate would decrease. So this concept, it hasn't changed, never will change, that we gave from the beginning. If you remember, also in the beginning, we gave the net energy change for a chemical reaction. Some reactions are exothermic, some are endothermic. And when you look at these, they're just looking at the starting position and the end position. It doesn't say anything about the process. The process is breaking bonds and making bonds. It's kind of like if you went from Spokane to Seattle, you have a net altitude change, a net potential energy change, but you go up and down hills as you travel from Spokane to Seattle. A chemical reaction, and when you look at reaction rates, we need to know what happens between the beginning and the end. So let's draw a potential energy scale like we did on slide number 2. So let's just say our reactants, they were right here. And we're having an exothermic reaction, so the products are down here. Remember, the very first thing that happens for reactants, you need to be able to break the bonds. That requires energy. It's kind of like if you wanted to go from the 3rd floor in our science building to the 2nd floor through a window, we have to go up in potential energy. Those reactants, they need to collide and gain some potential energy. And they need to get to a certain potential energy, enough energy to break the bonds. And so I made a dot here. This change, that's the energy required to break a bond. For any chemical reaction, there always needs to be an input of energy to get it started, to get that bond breaking process going. And it actually has a special name. That minimum energy to get it going is called the activation energy. It's different from chemical to chemical. It depends on how strong the bond is. It's kind of like your car. There's different bumper bond strengths. One car, you may be able to break the bumper off if you crash at 20 miles per hour. Another car, it may take 30 miles per hour. But every chemical reaction has an activation energy. And it's all a little bit relative, but we'll label it as E sub A. So those reactants need to collide with that amount of energy. When bonds are formed, energy is released. When things that are attracted to each other come together, when the bonding electrons and the nuclei come together, energy is released. So those reactants, they collide and gain some energy and then go up that hill, up that energy barrier, and they need that amount of energy to break the bonds. When bonds are being made, they lose energy. They release energy to the surroundings. So this is kind of like you going through that window. You're on the 3rd floor, got to climb up, get enough potential energy to go out the window, and then you can go down to the 2nd floor. This plot is showing the potential energy change during a chemical reaction. It has a special name. It's called a reaction diagram. And this is one for an exothermic reaction. So the delta H, it's still the same thing. It's the change of potential energy is between the reactants and products. So that's still our delta H. And it's still negative. We're going from maybe the 3rd floor to the 2nd floor. Energy is being released. But this whole diagram shows the process. There's always a positive input of energy that's needed. Activation energy always goes in the upward direction. It doesn't matter if it's exothermic like this or an endothermic diagram. And I can draw an example of an endothermic diagram. So for an endothermic one, the products are at a higher potential energy when the reaction is completed. But the reaction diagram, the reactants would need enough energy to break bonds. Energy is released when bonds are made. The activation energy, that peak up here, it's always above the final products. So from here down to there, that's our activation energy. Our delta H would be between the reactants and products, and in this case it would be a positive value. In an endothermic reaction, more energy is required to break the bonds than energy is released when bonds are made. An exothermic one is different. more energy is released when bonds are made than what's required to break the bonds. So, breaking bonds is the first step in a chemical reaction. As far as reaction rate, anything that you can do that can make it easier to collide in the correct orientation or to break a bond will affect reaction rate.
Shown on this slide is another embedded practice problem. Go ahead and pause the video and read through the problem and try and figure out what we're trying to solve. What the problem wants you to figure out is the final temperature when these two solutions are mixed. So the two main equations, delta H, the enthalpy change, that equals the Q of the system divided by the moles that actually reacted. So that's an equation. And we also have our Q equation, our Q of the surrounding equation. And remember, we're assuming that the surrounding material is the water. This is an aqueous-based solution. So we're assuming all the energy change occurs with the system and the surrounding water molecules, at least initially when the reaction first happens. Within the problem, you're given enough information to plug in every variable in these two equations except for temperature final. This is what we're solving for. The first equation we're going to use is the enthalpy change, and we know that delta H is negative 55,800 joules per mole. Using that, and if we knew how many moles reacted, we could figure out the heat flow. So how many moles actually reacted? Well, we're told in the problem HCl is an excess, which means the reaction stopped when that 14.1 milliliters of 0.996 molarity NaOH reacted. So with that volume and that concentration of sodium hydroxide, we can figure out how many moles of sodium hydroxide actually reacted. We need to figure out, with that information, how many moles of sodium hydroxide were used. If 1 mole was used, 55,800 joules would be released. But we need to figure out exactly how much reacted. Using the concentration and the volume that was used, we get the total moles of NaOH that reacted. And the total moles is 0.01404 moles of sodium hydroxide. We'll take that value and plug it into our delta H equation, and once we have that, we can solve for the Q of the system. How much energy flowed from the system, the reactants and the products. So taking this equation and solving for it, when that many moles, 0.014 moles of sodium hydroxide reacts, 783.432 joules worth of energy flows from the system to the surrounding water molecules. All the chemical energy from the system becomes the kinetic energy of the surrounding water molecules. And we'll assume all that energy is collected by the water. The Q of the system is negative because the system is losing energy. The Q of the surrounding is the same number but positive. The surrounding water molecules are gaining energy, so a positive number. So, we know the heat flow. We can use that number and plug it into our equation up here. The total volume is 46.4 milliliters, which means there's 46.4 grams of solution. And our assumption is that there's 46.4 grams of H2O. There's that many grams of water collecting the heat that's being released from the system. So we'll plug that in as our mass of H2O in our heat equation. So we have all the numbers in our equation and one variable to solve for, temperature final. So let's plug in the numbers. After plugging in all the various numbers, the temperature final, when we calculate it, is 25.6 degrees Celsius. So that number makes sense. It's an exothermic reaction. Heat is being released to the surroundings. We start at 21.6 degrees Celsius, so we have a higher temperature. So let's just kind of circle our last calculation. Go ahead and pause the video, read this practice problem, and try to determine what you're going to do. This is something new, kind of. I mean, you've done something like this before, but it's in the laboratory, but it's a little new with the materials. So pause the video, kind of, set up the problem in your mind, unpause the video when you're ready to make sure you're going in the right path. In this problem, you have two samples of water, and they're at different temperatures. One's at a higher temperature, one's at a lower temperature, and different quantities. But when you mix them together, what's the final temperature? So they're starting at different temperatures, but when they're mixed together, they should come to the same temperature. When you mix them together, one's losing energy, the other's gaining energy. And we'll assume that all the loss and gain stays with those water molecules. This is a Q problem. The Q of the water at 66.2 degrees Celsius and the Q of the water at 35.7 degrees Celsius. One's losing, one's gaining. So if we set up an equation, if one's losing and one's gaining, one of them, and it doesn't really matter what sign you put the negative side on, but one of them is losing and one is gaining. And our ultimate goal is to figure out that T final. That T final should be the same on both sides. Plugging in our equation for Q, the material is just water, so we're going to use the specific heat of water. The masses on both sides are slightly different. The temperature final on both sides are the same, but the temperature initials are different. After plugging in all the variables and the constants, the variable that we don't have is temperature final. So we're solving for T sub F. It's on both sides. So this is kind of like our X, but the variable is T sub F. Solving for that will give us our temperature final. So we need to rearrange the equation so we solve for T sub F. So the rest is just algebra. As we go through the algebra, we can cancel out some units. Grams and grams can cancel out, and that can happen on both sides. And we're going to be careful with our numbers and our units as we go through. And after one step of algebra multiplying through, here we are with some units and our variable we're trying to solve for. So here's our x, here's our T sub F, and we're trying to solve for that variable. The units there are joules per degree Celsius. The units here are joules. So be a little careful with your units as you go through. What cancels, what stays. The next step, we're going to rearrange and combine. We come up with this next relationship, still being careful with units. Next we can solve for, the next step is just to get T sub F by itself. We can see that we can cross off joules. Joules divided by joules cancels out, so we're left with only Celsius. We're going for temperature, so we probably did everything right because we just have a temperature unit, and it's in the denominator of the denominator, so it's in the numerator for our final answer. And after plugging that into our calculator, the final answer is 46.1. 46.1 degrees Celsius. Now, does that make sense? And, well, if we look at the starting temperatures of the two water samples, 46.1 degrees Celsius is in between the two temperatures. So it probably, well, we know it's right if I did it. We know it's between the high and the low, so it makes sense. And we also have a unit that makes sense. So, yeah, we did it right. Note that you did something very similar to this practice problem in the laboratory. In the laboratory, you mixed a hot metal with water, so it was two different materials. In this problem, it was mixing the same material, water, but the process is still the same. We're assuming there's a heat flow from something at a higher temperature to the lower temperature. And you can make an equation, relationships of Q values for either the same material or different material, and calculate some of the variables that are within those. Make sure you understand this and the one with the laboratory where you had a metal and water. I'm sure one of those will be on the final. On this slide is another helpful practice problem. Go ahead and pause the video, read the question, Unpause the video to make sure you're on the right path, and eventually we'll get the final answer. You're given a chemical reaction. There's 4 different chemicals that are part of it. Ultimately, you're going to calculate theoretically the enthalpy change for this reaction using the standard enthalpies of formation from your information packet. So let's go find those values. Carbon disulfide and carbon dioxide are both under the carbon heading. Make sure you look at the correct phase. The potential energy of carbon disulfide is different if it's a liquid, and those molecules are pretty close to each other versus a gas. In our chemical reaction, it's a liquid, so we're going to get the value that's a liquid. And carbon dioxide is a gas. It's a negative number, but remember this is relative to what we call our zero enthalpy. Let's go find oxygen and sulfur dioxide. O2 gaseous phase is still 0 as it was on our previous slide, and sulfur dioxide, which surprisingly is under sulfur, so that's sarcasm, but sulfur dioxide gas is negative 296.8. And remember, these units are kilojoules per mole. So we'll go ahead and write those numbers down below each chemical in the reaction. So we have the value for each chemical, but when they're part of a reaction, there could be 1, there could be 2, there could be 3, there could be more than that. So when we sum up all the potential energies of the products and all the potential energies of the reactants, we need to pay attention to the numbers that are before the chemicals in our balanced chemical reaction. Shown in green are the potential energies, the sum of the potential energies for the products, and in blue is the sum of potential energies for the reactants. So the 1 and 2 that are in the summation, again, that's how many molecules of each product molecule. And for the reactants, 1 and 3, that's how many there are of each reactant in this particular chemical reaction. Also note, just for your work, since oxygen is at 0, if you didn't want to show that in your equation when you do it on the exam, that's fine. And if you didn't want to show the 1 and just write 89.70, that's fine. We're just being more complete here as you're learning the process. As we do our calculations, so the change between the enthalpies of the reactants and the products, that change from reactants to products is a negative 1076.8 kilojoules per mole. Meaning if 1 mole of carbon disulfide reacted, that's how much energy would be released. Or, remember it's per mole, but if it was 3 moles of oxygen reacting, that's how much energy would be released. So mole of what? You have to look at which chemical you're talking about in the reaction. You should be able to look at this theoretical change at standard state conditions for the enthalpy and decide if it's exothermic or endothermic. So write that down. Pause the video and write that down. With all this information of potential energies, you should be able to write a diagram showing the potential energy changes. So your y-axis being the standard enthalpy of formation, which is proportional to the potential energy, which is proportional to the total enthalpy. You've already done the calculation on your calculator to get that change, the change of enthalpy for the reaction. But write in what are the sum of all the standard enthalpies of formation for all the reactants. So write in that number right here. Where are we starting at? So here's the sum of the potential energies for the reactants. So we're starting at a positive 89.7. So we'll put that number in there. The products are at a lower enthalpy. And that exact number, well, that's the sum of all the standard enthalpies of formations of the products. So we'll use that number and write that in down here. That sum of those three molecules is a negative 987.1 kilojoules per mole. So the theoretical enthalpy change, we start at 89.7 for the reactants, and the products they're at negative 987. That difference is 1076.8. What we're doing here is we're making a graph, or graphing the standard of enthalpies of formation change. Where they start, where they finish, and showing the change. This is something you should be able to do for any chemical reaction, this theoretical change. Go ahead and read this embedded practice problem. Unpause when you're ready to start working on the problem. In this example, instead of having a chemical reaction, you have a phase change. And CCl4, that's carbon tetrachloride. In this example, it's going from a liquid to a gas. So this would be no different than a pot of water on your stove becoming gaseous water. You can go to your information packet and find out the theoretical standard enthalpy of formation for carbon tetrachloride liquid. It's going to be somewhere on here. When it becomes a gas, what happens to that enthalpy? What's changing is those molecules that used to be pretty close to each other are moving further away. You should be able to think about that and decide whether the products are above or below. What's going on here? The molecules that are attracted to each other, they're moving further away. What's happening to the potential energies of those molecules? It'd be like moving you further away from the Earth. Another way to think about it, if you have some liquid water and you want it to become a gas, what do you have to do? Put it in the freezer or heat it up on the stovetop? With that in mind, you should be able to predict before you even start your process of getting a number calculation, is that positive or negative? So make that prediction, then go and find, using your information packet, the standard enthalpy of formation for each one, and then calculate the change. Pause the video, unpause when you're ready to see the final answer. This enthalpy change for this phase change should be positive. You need to add energy for a liquid to become a gas. The carbon tetrachloride liquid needs energy from the surroundings to become a gas. If something's gaining some energy, then that change is positive. That pot of water, that liquid's becoming a gas, you got to add heat from your stovetop. If you have evaporation of sweat on your skin, that liquid water that's on your skin, that's your sweat, for it to evaporate, well, it needs heat. It's getting that heat from your body heat. If you're moving two things away from each other, and that's what's happening here, liquid molecules away from each other, it requires energy. Okay, so from the information packet, 1 mole of carbon tetrachloride liquid is at negative 135.4 kilojoules per mole. The carbon tetrachloride in the gaseous phase, the standard enthalpy of formation is negative 95.98. That enthalpy is more positive than the enthalpy of the liquid phase. Okay, so they're both negative. Again, don't get hung up on that, but the gaseous phase is more positive. So to go from the liquid phase to the gaseous phase for carbon tetrachloride, that delta H, that enthalpy change for the process, is positive, which would be an endothermic process. As far as the true calculations, it's still final minus initial, the gaseous minus the liquid enthalpies. Plugging in our numbers, the enthalpy we calculate is 39.4 kilojoules per mole, a positive 39.4 kilojoules per mole. So enthalpy changes can be calculated for as long as there's a potential energy change or some sort of change in enthalpy, whether it's kinetic energy, pressure, volume, you can calculate an enthalpy change for the process. So this was going from a liquid to a gas, and this is called vaporization. This delta H, since it's for something that's kind of specific like this, it has a certain name. It's called the heat of vaporization. And when we label delta H in subscript, if it's going from a liquid to a gas vaporization, it's delta H subscript VAP, standing for vaporization. So anywhere we wrote delta H in this problem, since it wasn't a chemical reaction, it was this particular process, we can put VAP subscript. If you didn't do it, that's okay, but I'm going to put that in a few places just to illustrate that's what you can do. On this slide is an example problem. Go ahead and read the problem, pause the video, read the problem, unpause when you're ready to see the answer. As you read through the problem, the ultimate thing you need to calculate is how much energy is produced when 1 gram of reactant nitrogen oxide, so NO, when it reacts. So that's all you have. What else does it say? Well, you're told that you need to calculate the enthalpy change from the standard enthalpies of formation from your information packet. So this is a two-part problem. You need to theoretically calculate what the enthalpy change would be at standard state conditions, and then once you have that energy, how many kilojoules per mole, then you can do the stoichiometry problem starting with your grams of A and eventually figuring out, your B is how much energy. Let's calculate the change of enthalpy first. From our information packet, we see that the nitrogen oxide is 90.29 kilojoules per mole. Oxygen, O2 gas is still at 0, just like we've seen in other practice problems. And nitrogen dioxide, it's at a lower enthalpy, 33.10. So the reactants have more enthalpy than the products. So even before we do a calculation, we can tell that the change for the reaction should be negative. And that change is a negative 114.4 kilojoules per mole. So this is an exothermic reaction. That's the first part of the problem. The next part is our stoichiometry problem. If 1 mole of oxygen reacted, a negative 114.4 kilojoules would be released. But what if 1 gram of nitrogen oxide? So that's our A. We're starting with our A, and ultimately we're going to go to how much energy would be produced, since it's an exothermic process. I'm going to take it all the way to kilojoules. You can go to any energy unit, it's not specific, but my final answer will be in kilojoules. Using the molar mass of nitrogen oxide, we can get how many moles are reacting, and then using our chemical reaction, we can calculate the amount of kilojoules that's going to be produced. And there's the molar mass relationship in green, and the chemical reaction, the mole to mole to mole to energy relationship. And remember, the negative, if you choose to show it on next to the negative 114.4, it's okay if you show it or not. Again, the negative is just illustrating the process. I'm going to include it when I do my stoichiometry setup. After figuring out how many moles of NO reacts, we see it's a lot less than 1. If we keep that in mind as we're getting our final answer, that relationship says for every 2 moles of NO that reacts, 114.4 kilojoules would be produced. Well, it's a lot less than 2 moles. So our final answer should be less than 114 kilojoules. Our relationship is 114.4 kilojoules produced for every 2 moles of NO that reacts. And again, that 2 comes from the chemical reaction. That 2 comes from that 2. The final answer is almost 2 kilojoules worth of energy is released, 1.91 kilojoules. And since I decided to put a negative on my ratio, I'm going to get a negative 1.91. The system is losing chemical energy, and the surroundings is taking in that energy, absorbing that energy. Yet another practice problem for you. Go ahead and read the problem and unpause when you're ready to get started. This one's a little different. This one's a little different because you're told how much energy you want to acquire, 293 kilojoules of heat. So this time your A is the energy. Your B is how much of one of the molecules needs to react. Your B is the ethanol. The problem asks for the volume, and you can give it in any volume that you want, gallons, liters. But if you look within the problem, you see the density, and that's grams per milliliter. Since we have that, my final answer for volume is going to be in milliliters. Let's pause the video. You know what you're starting with, you know where you're going to. Go ahead and write a flow of units you're going to go between, and think about what relationships can be used to go between the various units. So let's pause the video, unpause once you have kind of your flow of your stoichiometry problem. For some process, we need 293 kilojoules. The chemical reaction says for every 1 mole of ethanol that reacts, you can get 1235 kilojoules. The chemical reaction gives you a relationship between energy and moles of the ethanol. Then we know molar mass can be used to go between moles and grams, so we can use the molar mass of ethanol to determine how many grams of ethanol needs to react. And density gives us a relationship. It gives us a mass-volume relationship. Once we have grams of ethanol, we can use its density to figure out the volume. Mole, gram, and milliliter units of ethanol, it's the same amount of ethanol, but it's just getting it into the unit that's needed. When I start this stoichiometry problem, we're all starting with 293 kilojoules. When you start with it, you can make it positive or negative. It doesn't matter, as long as you are consistent on how you treat your delta H in your proportion. I'm going to start out with negative 293 kilojoules just because it's an exothermic process, but if you decided to start with positive 293, that's okay. When I'm finished though, milliliters should be positive no matter what. The quantity, the mole quantity, the gram quantity, the milliliter quantity should be positive numbers. So since I'm going to put a negative in front of the 293 kilojoules, when I do my mole to kilojoule relationship, that energy needs to have a negative next to it. If you wanted to start with a 293 kilojoules, then the relationship should be 1 mole per positive 1235 kilojoules. The amount of moles needs to be a positive number. Either way is fine. However you decide to start, just be consistent when you do. The chemical reaction tells us that for every 1 mole of ethanol that reacts, 1235 kilojoules worth of energy would be released. So we put that proportion in, and if we need 293 kilojoules, then we need around 0.237 moles of ethanol. So that's the mole quantity. Eventually we need to get to milliliter quantity. Next in line is the molar mass, and after we plug that in and calculate, our number on the calculator would be around 10.9 grams. We need that much in gram quantity. Lastly, we'll use density to see what volume quantity of ethanol we need. And after tagging along that relationship, your calculator, your determination will tell you need about 14 milliliters. 13.8 milliliters of ethanol. Shown on this page is an example problem, and it's related to specific heat and heating an iron pan. Go ahead and pause the video, unpause when you're ready to check your answer. So we have an iron skillet, an iron pan, so it's 100% iron, and it's heated to a really high temperature. The question wants to know what's the heat from the iron if it cools to a lower temperature. So that Q of the iron. How much heat flows from the iron when it starts at that high temperature and cools to that room temperature? You should be able to say whether that Q is positive or negative even before you do a calculation. And as we think, it's losing energy, the iron's losing energy, so if it's losing, it's negative. That Q for the iron should be negative. We're going to use our Q equation, and it's for a specific material, so we'll use the Q equation that has specific heat. We'll need to go to our information packet to find the specific heat of iron, and we've done a lot of problems with water, but this one is iron. And when we go to our information packet, we see that the specific heat of iron is 0.449 joules per gram per degree Celsius. Those units in the specific heat tell us what units our variable should be in, so the mass of iron needs to be in grams, and the temperature needs to be in Celsius. Temperature's already in Celsius, but the kilograms of iron, that needs to be converted into grams. 1.63 kilograms of iron, well, 1,630 grams of iron. Temperature final minus temperature initial, we better have our negative there. Final is 21 degrees Celsius. The initial temperature it started at was 178 degrees Celsius, which will give us a negative temperature change, which will make the Q a negative number, which makes sense. The iron is losing energy. And when you do your calculation, it's a negative 114,903 joules. So that iron cooling from that high temperature down to room temperature, that's how much energy it releases. And just again as a frame of reference, your body metabolizes and loses about 10 million joules worth of energy per day. So you lose more energy than that iron pan cooling. You don't start at that temperature, but throughout the whole day you lose more energy. Let's pause the video again and do another example problem. Unpause the video when you're ready to see the final answer, or if you need help as you go through the process. So as you read through, you're given reactant quantities of both reactants. So 10 grams of each one. If you're given quantities of both and you want to figure out how much energy is produced, well, this looks like a stoichiometry problem, but how much reacts if we have two A's? Well, we need to figure out the limiting reagent. I know there's different ways to figure out limiting reagent, but on the exam you need to show a way. The way that we're going to show it here is we're going to start with each quantity of reactant and separately figure out how much product is being produced. Remember, the one that produces the least amount of product is your limiting reagent. The product I'm going to go to is CCl4, carbon tetrachloride. Once we figure out which one is the limiting reagent, then we can use the delta H, the enthalpy change, to figure out how much energy is being produced for this exothermic reaction. Starting with 10 grams of each reactant and using their respective molar masses, we have about the same starting mole quantity of each reactant. But again, to get limiting reagent, show how much product is being produced. So we have moles of reactants. Next we'll use the mole-to-mole relationships to get to moles of a product. And the one we're going to is carbon tetrachloride. Since number-wise 3 chlorines are used for every 1 carbon disulfide, number-wise the chlorine is used up faster. And 10 grams of chlorine gas will only produce 0.047 moles of carbon tetrachloride, and that's when the reaction will stop. 10 grams of carbon disulfide could make up to 0.13 moles of the product of carbon tetrachloride, but not all of it can be used up because the reaction will stop when the chlorine is used up. So the limiting reagent is chlorine. Okay, we need to figure out how much heat is released in this exothermic process. We can use anything that's part of the limiting expression. So we could start with any of those quantities. We could start with 10 grams of chlorine, we could start with 0.1410 moles of chlorine, or start with 0.04701 moles of carbon tetrachloride. We know this amount was formed, so we could use its mole to energy relationship, or we know this mole quantity of chlorine was used up. We could start with either one of those numbers. When I do it, I'm actually going to show, I'll show it both ways. So my first one, I'll start with the product. We know that many moles, 0.04701 moles of carbon tetrachloride were formed. And we know from the chemical reaction, for every 1 mole of carbon tetrachloride that's formed, 230 kilojoules of energy is released. So we'll use that ratio. Since I've done it for all my other problems that were exothermic, I put a negative there. I'm going to do it for my problem. But just remember, you don't have to put that negative there. But when we do that math, the energy that's released is 10.8 kilojoules. We could have also started this problem with the moles that were used up, and we should get the same amount of energy. So I'm going to show it both ways. I don't expect you to show it both ways on the exam, but I want to show you just so that you can see that it should be the same. So hopefully, our starting numbers are different, and hopefully our proportion or relationship is also different so that we get 10.8 as our final answer. The chemical reaction says for every 3 moles of chlorine that reacts, 230 kilojoules worth of energy is released to the surroundings. We're going to use those numbers for our relationship, for our proportion. And when you do that math, you get exactly the same number, negative 10.8 kilojoules. If 10 grams of chlorine gas reacts, 10.8 kilojoules worth of chemical energy is lost to the surroundings. Even though the answer didn't ask this, that negative 10.8 kilojoules, that's Q of the system. The system, the reactants lost energy. Whatever the surrounding material is, the Q of the surrounding, it gained that energy. Q of the surroundings would be a positive number. That we'll circle that. That's a little bit of extra, even though the problem didn't ask that. But that's the heat flow.